566 million years ago, our planet was an ever-shifting canvas of evolution and chaos. Giant trilobites crawled across the seafloor long before the first dinosaur roared. Supercontinents like Gondwana and Pangaea formed and broke apart through incredibly slow continental collisions. Lush fern forests once blanketed polar regions, while deserts emerged where oceans had flooded the land. Each era brought new life forms, some bizarre, others beautiful, many destined to vanish. The Cambrian period was the opening chapter of the Paleozoic era and a crucial part of the Phanerozoic eon, when life truly began flourishing in visible, complex forms. It lasted about 51,950,000 years, starting roughly 538,800,000 years ago and ending around 486,850,000 years ago when the Ordovician began. Earth looked completely different then. Most land sat in the southern hemisphere, surrounded by the vast Panthalassa Ocean. Meanwhile, the giant supercontinent Gondwana was taking shape. As its pieces collided and merged during the Ediacaran and early Cambrian, tectonic movement created new mountain ranges and triggered volcanic activity along the continent's edges. These changes drove global temperatures higher. Another landmass, Laurentia, sat near the equator, separated from Gondwana by the widening Iapetus Ocean. But the most remarkable thing about the Cambrian was what happened to life itself. Before this period, most organisms were tiny, single-celled creatures whose fossils are extremely rare. By the end of the Ediacaran, some complex, multicellular organisms had begun appearing. Then, something extraordinary happened in the Cambrian explosion. This was a sudden burst of diversity and complexity that produced the first representatives of nearly all major animal groups we know today. The Cambrian is also marked by numerous Lagerstätten, special fossil sites preserving not just hard shells, but even soft tissues. These deposits give us exceptionally detailed glimpses of early life. The word Cambrian comes from the Latin form of the Welsh name for Wales, Cambria. Welsh rocks of this age were first seriously studied there. In 1835, geologist Adam Sedgwick named the Cambrian and divided it into three parts: lower, middle, and upper. Together with geologist Roderick Murchison, he tried drawing the boundary between Cambrian and the overlying Silurian layers. They initially agreed, but it didn't last. Since early Cambrian rocks contained few fossils, Sedgwick identified his Cambrian layers mainly by rock types. Murchison, meanwhile, found more fossils in Silurian rocks and used them to correlate layers across Europe and Russia. As scientists discovered fossils in older rock layers, Murchison began pushing the lower boundary of the Silurian into territory Sedgwick considered Cambrian. A genuine tug-of-war over the boundary erupted between their scientific schools. Things got messier in 1852, when new fieldwork revealed a clear break in Silurian rocks. Differences in fossil composition let Sedgwick reclaim some disputed layers for the Cambrian. The argument outlasted both men. Finally, in 1879, geologist Charles Lapworth intervened, carving out the contested layers as a completely new period, the Ordovician. The term Cambrian was officially adopted in 1960 at the 21st International Geological Congress. Today, it covers only what Sedgwick originally called the Lower Cambrian, though its lower boundary now extends into even older rocks. To correlate rock sequences worldwide, geologists use a system of global boundary stratotype sections and points. These are specific locations on Earth where the start of a given geologic time unit is clearly recorded in rock layers. The Cambrian period divides into 4 major subdivisions, called series, and 10 smaller stages. Scientists initially thought the Cambrian began with the appearance of trilobites, ancient armored relatives of modern arthropods. But later discoveries of small shelly fossils and Ediacaran organisms pushed the timeline back, requiring a more precise starting point. The official definition of the Cambrian period came only in 1994. Scientists chose the Fortune Head section in Newfoundland, Canada. The base of the Cambrian there is marked by the appearance of fossil traces called Treptichnus pedum, burrows indicating more complex animal behavior. Early estimates placed the Cambrian start at roughly 570 million years ago, but newer, more accurate dating methods put it at 538,800,000 years ago, give or take 600,000 years. This date comes from volcanic ash layers in Oman, which also show a drop in carbon-13 content and the disappearance of characteristic Ediacaran organisms like Claudina and Namacalathus. Some researchers believe this section may not reflect the true boundary and prefer earlier estimates of 544 to 542 million years ago. In Russia, many paleontologists prefer to mark the Cambrian's beginning with the start of the Timoteian stage, characterized by the appearance of mineralized skeletons and the first Archaeocyathon reefs. The Cambrian period consists of 4 parts. The Terranuvian series spans from 538,800,000 to roughly 521 million years ago, the earliest chapter of the Cambrian, with no trilobite fossils yet. It includes the Fortunian stage and a second stage still unnamed, characterized by trace fossils and small shelly fauna. The Terranuvian series name was officially approved in 2007. The second Cambrian series, roughly 521 to 506,500,000 years ago, still lacks an official name. It includes the third and fourth Cambrian stages. Animal diversity surged during this time, especially among trilobites and Archaeocyathons. Correlating deposits from different regions is difficult due to variations in fossil composition. The Meolingian series, roughly 506,500,000 to 497 million years ago, was formerly called the Third Cambrian series. It includes the Wuluan, Drumian, and Guzangian stages. It was formally established in 2018 and named after the Miaoling Mountains in China. The beginning of this series is marked by the appearance of the trilobite Oryctocephalus indicus. At the boundary of the second Meolingian series, many trilobite groups went extinct, including Olenellids, Eodiscids, and Redlichiids. This is considered the first known mass extinction of trilobites. The Furongian series spans from roughly 497 to 486,850,000 years ago. It represents the final portion of the Cambrian. The name was formalized in 2003, replacing the former term Upper Cambrian. It begins with the appearance of the trilobite Glyptognostus reticulatus and contains the Pabian, Jiangshanian, and a still unnamed 10th stage. The Cambrian Ordovician boundary is officially set at Green Point in western Newfoundland, Canada, and dates to approximately 485,850,000 years ago. It's defined by the first appearance of tiny tooth-like fossils called Iapetegnathus fluctivagus. Where this fossil isn't found, scientists use other markers like planktonic graptolites or the trilobite Jujujaspis borealis. During the Cambrian period, Earth experienced several major meteorite impacts. Around 535 million years ago, a large collision created the Cardla crater in Estonia, roughly 20 kilometers in diameter. The Gardnose crater in Norway, about 5 kilometers across, formed approximately 500 million years ago in shallow water. Cambrian climate was predominantly warm and humid. Scientists deduce this from characteristic sediments and rocks, tropical carbonate platforms, reefs built by ancient sponge-like organisms called archaeocyathans, and bauxite deposits that form in warm, moist conditions, along with evaporites and calcretes typical of dry, arid regions. The widespread distribution of such deposits, especially in tropical zones at various latitudes, shows Earth was in what scientists call a greenhouse climate state. There were no large ice sheets, and high temperatures persisted across much of the planet. By the end of the Cambrian, fossil evidence from trilobites indicates only minimal temperature difference between poles and equator. Even polar regions weren't very cold, and heat was distributed fairly evenly across the planet. Some scientists found traces of ancient glaciers in Avalonia, which then sat in high southern latitudes, though debate continues whether these glacial deposits truly formed during the Cambrian or belonged to the slightly earlier Neoproterozoic. Actual temperature estimates for the Cambrian vary by research method. Some calculations suggest average global temperatures may have exceeded 40 degrees Celsius. However, more reliable models combining multiple data sources give a more moderate value, around 20 to 22 degrees Celsius at the very beginning of the Cambrian, rising to approximately 23 to 25 degrees for the remainder of the period. This prolonged warmth was closely tied to high atmospheric carbon dioxide levels. One major cause was the formation of the massive supercontinent Gondwana. As land masses converged and tectonic plates shifted to form new boundaries, volcanism intensified along them. These eruptions released enormous volumes of greenhouse gases, including carbon dioxide, heating the planet even further. The Chalkoringi magmatic province was a major geological event. Its eruptions began around the fourth stage of the Cambrian and lasted into the early Meolian. Massive amounts of carbon dioxide, methane, and sulfur dioxide entered the atmosphere, driving sharp climate shifts and heating the ocean surface. Scientists still debate how much the oceans actually warmed, using oxygen isotope ratios in ancient marine rocks to estimate temperatures. Interpretations vary widely. Tropical surface waters may have ranged from 28 to 32 degrees Celsius, or perhaps 29 to 38. Today's tropical seas average around 26 degrees. Despite the heat, atmospheric oxygen was far lower than now. Though oxygen had been rising since the Neoproterozoic, thanks to photosynthetic organisms, Cambrian levels fluctuated between roughly 3 and 14%, well below today's 21%. Low oxygen combined with warm oceans meant less dissolved oxygen in seawater, especially at depth, creating anoxic zones nearly devoid of oxygen. These oxygen-poor environments shaped early animal evolution. As organisms began burrowing into seafloor sediments, they mixed layers, bringing oxygen-poor material up to oxygen-rich surface waters. This bioturbation reduced burial of organic carbon and sulfur, making it harder for oxygen to accumulate in the atmosphere and oceans, and spreading underwater oxygen deficits. Meanwhile, intensified weathering on continents delivered more nutrients to the ocean, fueling phytoplankton blooms that supported complex animal life. But excessive blooms caused eutrophication. Too much organic matter decayed, consuming oxygen and starving the water.
These oxygen cycles shaped life on Earth. Higher oxygen meant greater biodiversity, larger and more active animals, complex ecosystems, and expanded habitable seafloor. When oxygen dropped due to sea level changes, shifting currents, or upwelling of oxygen-poor deep water, mass die-offs followed, sometimes regional, sometimes global. The Cambrian was a time of extreme environmental swings, and the alternation between oxygen-rich and oxygen-poor conditions drove evolutionary innovation. Some species vanished, while others adapted in increasingly unusual ways. As for plants, there were almost none on land during the Cambrian. Marine vegetation differed little from what existed shortly before in the Ediacaran period. Its main representatives were large algae, including Fusianospira, Cynosolindra, and Marpolia. Notably, no calcareous algae containing calcium carbonate have been found from this time. Nor are there any Cambrian fossils of land plants, which scientists call embryophytes. However, microorganisms thrived on land. Around 500 million years ago, biofilms and microbial mats already covered tidal flats and beaches. These microbial communities played a role similar to modern desert soil crusts, stabilizing surfaces and promoting early soil formation. Genetic data suggest arthropods, the future group of insects, spiders, and other animals, may have begun colonizing land during the Cambrian. But as with land plants, the oldest reliable fossils of terrestrial arthropods date to the Ordovician, so their Cambrian origin remains disputed. The Cambrian explosion was a time of extraordinary change and rapid development in Earth's history of life. It occurred roughly 541 million years ago and opened a new chapter when life became noticeably more complex and diverse. During this period, many animal groups developed rapidly, especially multicellular organisms. Most Cambrian creatures lived in the ocean. For a long time, scientists believed trilobites, ancient marine creatures with hard shells, were the most abundant animals of that time. But newer research revealed a somewhat different picture. Trilobites certainly played an important role, but were only part of a much larger group of arthropods, which includes insects, crabs, spiders, and many other animals. Arthropods truly dominated Cambrian seas, though many had soft, fragile bodies that preserved poorly as fossils. Trilobites, in contrast, had sturdy armor made of calcium carbonate, the same substance found in many seashells. Such armor preserved well, making trilobites appear far more numerous in the fossil record than they actually were. This period marked a turning point for life on Earth. The number and diversity of species increased sharply, but not all life forms survived the transition. The Ediacaran biota, soft-bodied organisms that existed before the Cambrian, suffered mass extinction. Around the same time, new animal behaviors appeared, especially burrowing into the seafloor. These burrowing organisms irreversibly changed the bottom environment. Previously, the seafloor was mainly covered by thick microbial mats, like slippery blankets of microorganisms. But by digging tunnels through the sediment, animals disrupted and eventually destroyed many of these mats. This process is called bioturbation. Organisms that depended on microbial mats had to either adapt or disappear. Those who managed to adapt began exploring new habitat types that emerged in the disturbed seafloor sediment. During this same time, animals with hard, mineralized body parts like shells appeared more frequently. Among them were representatives of most major animal groups we recognize today. One example is bryozoans, tiny colonial creatures previously thought to have emerged much later in the Ordovician. However, most of these early animals were just primitive precursors to modern forms.
Additionally, mineralized animals typically lived on the seafloor and don't reflect the full diversity of soft-bodied life, which may have been far more abundant. Though the early Cambrian was a time of incredible flourishing, earning it the name Cambrian explosion, this surge couldn't last forever. Around 515 million years ago, things began to shift. Species disappearing outnumbered those emerging. After roughly 5 million years, total genera dropped from about 600 to 450. New species formation rates fell to 1.5 or 1.3 times previous levels. Around 500 million years ago, ocean oxygen levels plummeted sharply. This triggered hypoxia, a state where oxygen is insufficient for most animal survival. Simultaneously, toxic hydrogen sulfide levels rose, and this dangerous combination led to another extinction event. The second half of the Cambrian proved much quieter and biologically poorer than the first. Several rapid extinction waves occurred. Reef-building archaeocyaths, sponge-like organisms that had previously displaced older reef builders like stromatolites, eventually vanished too. After their disappearance, stromatolites briefly returned, but overall biodiversity remained low until the Great Ordovician biodiversification event later sparked new life flourishing. Life in Cambrian oceans was challenging. Oxygen content often stayed low and unstable.
When oxygen-depleted deep waters occasionally rose to shallow areas through upwelling, entire communities could perish. Yet these same stressful conditions drove evolution forward and ultimately contributed to biodiversity growth. Interestingly, some Cambrian animals even began exploring land, evidenced by preserved trace fossils. Two such trace types are called protychnites and climactychnites. Scientists believe at least some protychnites were left by extinct arthropods called euthocarcinoids. As for climactychnites, fossils of the actual creature haven't been found yet, but the trackways and resting impressions suggest a large, soft-bodied being, possibly resembling a giant slug or early mollusk. Compared to later Earth history periods, Cambrian animal diversity remained fairly limited. Free-swimming creatures in the water column were rare. Most animals lived on or just above the sea floor. Animals with mineralized shells or skeletons were also less common than in later times, partly due to ocean chemistry unfavorable for forming and preserving hard body parts. Despite these limitations, the Cambrian left us some of the most remarkable fossil discoveries in all paleontology history. Some fossils preserve not just hard parts, but also soft tissues, skin, gills, and digestive systems, which almost never make it into the paleontological record. These exceptional sites, called Lagerstätten, offer an unusually detailed glimpse into ancient life. The most famous include Sirius Passet in Greenland, the Sinsk biota in Russia, the Maotianshan shales in China, the Emu Bay shales in Australia, and the Burgess Shale in Canada. The Ordovician is another fascinating chapter in Earth's ancient history. It was the second period of the Paleozoic era, and the second of 12 major periods in the Phanerozoic Eon, the vast stretch of time covering most of complex life's history on Earth. The Ordovician lasted about 41,600,000 years, beginning roughly 486 million years ago, right after the Cambrian ended, and closing around 443 million years ago, when the Silurian began. The name Ordovician comes from the Ordovices, a Celtic tribe that once lived in what is now Wales. British geologist Charles Lapworth officially named the period in 1879. At the time, two other geologists, Adam Sedgwick and Roderick Murchison, were arguing over which period certain rocks in North Wales belonged to. Sedgwick placed them in the Cambrian, Murchison in the Silurian. But Lapworth noticed something important. The fossils in those rocks differed from both Cambrian and Silurian ones. To settle the dispute, he proposed a completely new period, the Ordovician. Only in 1960, about 40 years after Lapworth's death, did the International Geological Congress officially recognize the Ordovician as its own geological period. During the Ordovician, ocean life didn't just survive, it flourished. The great surge in diversity that began in the Cambrian continued. Oceans teemed with invertebrates, especially mollusks and arthropods. Arthropods played a particularly important role, and some may have begun venturing onto land, though they wouldn't fully establish themselves there until later in the Devonian. Around this time, the first land plants appeared, small and simple, but heralding enormous changes to come. One of the most significant events was the Great Ordovician Biodiversification event, when life's variety exploded. Fish, the first true vertebrates, began to develop during the Ordovician, and by the end of the period, the first jawed fish may have appeared. At the same time, something unusual was happening in the sky. During the Ordovician, Earth was struck by roughly 100 times more meteorites each year than today. This strange phenomenon, called the Ordovician meteor event, may have been caused by a temporary ring around Earth, some scientists suggest. The early Ordovician climate was extremely hot. Earth was in a greenhouse state, with ocean surface temperatures comparable to the early Eocene climatic optimum, a much later warm period. Early on, the atmosphere held vast amounts of carbon dioxide, but then things began to shift. By the late early Ordovician, the planet started cooling, and by the middle Ordovician, the climate became more moderate. Eventually, Earth entered a prolonged cold phase known as the early Paleozoic Ice Age, which may have begun as early as the Floacian Age, or slightly later, in the Dipingian or Sandbian. During the Dipingian and Sandbian ages, there were also periods of heavy rainfall, evidenced by metal traces in ancient rocks of the region now called Baltica Scandia. Then, in the early Caesian Age, temperatures briefly rose again during the so-called Boda event, which promoted the formation of reef-like structures and the rapid spread of marine life across what is now Europe. Another wet period occurred in the early Caesian Age. After this, Earth cooled again, and at the very end of the Ordovician, a major glaciation began, known as the Hernantian. In the Ordovician, sea levels were higher than in any other period of the Paleozoic era. The continents were predominantly low and flat, so vast areas were flooded by shallow seas. These waters were especially favorable for animals that built hard shells and skeletons from calcium carbonate. In the early Ordovician, sea levels continued to rise and remained high during the middle of the period. Despite occasional local drops, the overall upward trend persisted into the beginning of the late Ordovician. Then, a few million years before the Hernantian glaciation, as Earth cooled, sea levels began to decline steadily. During the glaciation itself, seas advanced and retreated repeatedly, though the exact sequence of these changes hasn't been established yet. Some scientists believe sea level fluctuations started before the official beginning of the Hernantian glaciation, but reliable evidence of glaciers appears only at the very end of the period. Today, it's proven that during Hernantian times, glaciers existed in territories of present-day Africa and South America, which were then near the South Pole.
these southern lands formed the base of that era's ice caps. Like North America and Europe, the giant southern continent Gondwana in the Ordovician was also largely covered by shallow seas. Warm, sunlit waters gave marine organisms space to grow and build reefs and carbonate platforms. The enormous ocean Panthalassa occupied most of the northern hemisphere, and other ancient oceans existed nearby, including Prototethys, Paleotethys, and the Conti Ocean, which disappeared by the end of the period. Among them were also the Iapetus Ocean and the newly forming Rheic Ocean. For most of the late Ordovician, oceanic life flourished. Many groups of marine animals developed successfully, and ecosystems became increasingly complex. But toward the end of the period, everything changed drastically. A series of major extinctions followed, wiping out countless sea dwellers. Tiny, tooth-like conodonts and floating graptolites were especially hard hit. Two entire orders of trilobites, agnostids and asaphids, disappeared completely, while only a small number of other forms survived.
Other marine animals suffered heavily too. Brachiopods, resembling bivalve mollusks, colonial bryozoans, and echinoderms, relatives of sea stars and sea urchins. Endocerids, squid-like cephalopods, nearly vanished entirely. In the following Silurian period, only rare representatives remained. Scientists believe this mass extinction may have been caused by the sharp glaciation at the end of the Ordovician. Possibly, the cooling was linked to the spread of the first land plants, which began extracting carbon dioxide from the atmosphere and thereby changing Earth's climate. The final part of the Ordovician became one of the coldest episodes in the last 600 million years of Earth's history. Despite mass extinction, the Ordovician gave rise to an incredible variety of new marine life that shaped the rest of the Paleozoic. The oceans teemed with filter feeders, straining tiny food particles from the water. They formed simple food chains and lived in tightly knit communities. Ordovician life was far more diverse and complex than in the early Cambrian, and many features of these marine ecosystems persist today. One of the greatest events of this era is called the Great Ordovician Biodiversification Event. Though less famous than the Cambrian explosion, it was just as significant. During this time, the number of marine animal genera quadrupled, representing about 12% of all known marine fauna in the Phanerozoic eon. Many animals became smaller than their Cambrian ancestors, while filter feeders spread more widely than ever before. The old Cambrian fauna, inarticulate brachiopods, archaeocyathans, eocrinoids, and early trilobites, gradually gave way to new groups. In their place came articulate brachiopods with hinged shells, crinoids or sea lilies, and numerous cephalopods, relatives of modern squids and octopuses. Articulate brachiopods spread especially widely across continental shelves, displacing trilobites in many areas. These changes reflected a sharp increase in animals forming hard coverings from carbonate minerals. Continental positions in the Ordovician strongly influenced which animals developed in different regions. Various areas developed their own unique invertebrate communities. For example, Laurentia and Baltica, located in the tropics and surrounded by warm, shallow seas, had their own trilobite groups, distinct from those in Gondwana. Even within Gondwana itself, fauna differed between warm and cool areas. Some Central Asian regions, like Tian Shan, were closely linked faunally with Gondwana. The Elburz region in modern Iran also had connections with South China. Southeast Asian marine fauna was closely tied to Gondwana as well. North China combined faunal features from Laurentia and those South American regions that were part of Gondwana. Additionally, there existed a distinct group of animals from the so-called Celtic province. However, some animals, like tropical articulate brachiopods, were distributed worldwide and not limited to specific regions. With the onset of the Middle Ordovician, marine animals began spreading more actively across the planet. As a result, regional faunas became less isolated and increasingly overlapped, especially as oceans like Iapetus shrank. Nevertheless, regional differences in marine life persisted until the very end of the Ordovician. Trilobites, armored marine arthropods with jointed limbs and multiple eyes, were especially numerous and diverse. In the Ordovician, they evolved rapidly and acquired many unusual features. Some developed long spines and knobs for protection against predators. Early sea scorpions, eurypterids, and predatory cephalopods. One trilobite, called Hypsiparisk, even adapted to swimming. Others developed broad front sections of the head, useful for burrowing in seafloor mud. Trinucleids had unusual, flat, pitted margins on their head shields. Some trilobites, like Asaphus kowalewski, acquired long eye stalks, allowing them to spot predators earlier, while others lost their vision entirely. By the end of the Ordovician, early arachnids, relatives of spiders and scorpions, may have already begun moving onto land. Solitary coral polyps had existed since at least the Cambrian, but large reef-building corals emerged in the early Ordovician, alongside the first known soft-bodied octocorals. The growth of coral reefs was accompanied by an increase in animals using calcium to build shells and skeletons. Brachiopods reached incredible diversity and adapted to nearly all marine conditions, from shallow coastal waters to deep ocean depths. Mollusks, which appeared in the Cambrian or possibly earlier, also became more numerous and acquired many forms and sizes, including bivalves, gastropods, and straight-shelled cephalopods that spread from shallow tropical seas across almost the entire ocean. Graptolites, tiny colonial animals floating in the water column, thrived throughout this time. New groups of crinoids and cystoids, ancient echinoderms, also appeared. While it was previously thought that the first true fish arose in the Ordovician, finds from China show that jawless fish, ostracoderms, probably existed as early as the Cambrian. The first jawed fish, gnathostomes, may have begun appearing in the late Ordovician. Tiny flask-shaped microfossils called Chittenozoans, first appearing in the late Cambrian, experienced a true flourishing in the early Ordovician and rapidly spread worldwide. At the start of the Ordovician, trilobites were joined by many new marine animals, including tabulate corals, new groups of brachiopods, strophominids and rhynchonolids, bryozoans, conodonts, and numerous mollusks and echinoderms. Among them appeared the first ophiuroids and true sea stars. Arthropods remained abundant, with old Cambrian trilobite orders persisting alongside a new order, the Phacopids. The Ordovician also saw the earliest evidence of land plants, marking the beginning of a major restructuring of Earth's ecosystems. In the Middle Ordovician, marine communities began to change. Trilobites lost their former dominance as ecosystems became more balanced and diverse. Brachiopods, bryozoans, mollusks, and echinoderms flourished. Corals also became more diverse, with tabulates spreading widely and the first rugose corals appearing. Planktonic graptolites continued to diversify with the emergence of a new group, the diplograptids. One of the oldest known armored jawless fish, Arandaspis, lived during this time. The Middle Ordovician also saw a sharp increase in animals that drilled through hard materials like shells and rocks, a phase called the Ordovician bioerosion revolution. This is evidenced by the sudden appearance of many drilling traces known as trypanites, paleosabella, petroxestes, and ospreonides. Bioerosion became an important factor, especially for animals with thick shells, corals, bryozoans, and brachiopods, as well as for the extensive hard carbonate seafloors widespread during this era. By late Cambrian times, and even more so in the Ordovician period that followed, green algae had become quite common. Scientists consider them the ancestors of the first land plants. Somewhere around the middle or end of the Ordovician, over 460 million years ago, tiny soft-bodied plants began appearing on land, resembling today's liverworts. These early plants lacked vascular systems, so they couldn't transport water and nutrients throughout their bodies the way most modern plants do. Fossil spores from Ordovician rocks look like spores from bryophytes, the group that includes mosses and liverworts today. Along with the first land plants, some of the oldest fungi began thriving, including arbuscular mycorrhizal fungi from the glomerulines order. These fungi formed a crucial partnership with early plants, connecting to the roots. While receiving sugars from the plants, the fungi helped extract minerals from the soil and transfer them to plant cells. This cooperation, called mycorrhizal symbiosis, was essential for plant survival on land. Fossils of these fungi, including thread-like hyphae and tiny spores, have been found in Ordovician rocks in what is now Wisconsin. These finds are about 460 million years old. Back then, the land remained nearly empty except for simple moss-like plants and their fungal helpers. Meanwhile, in the oceans, stromatolites still existed, unusual layered structures created by microorganisms, mainly bacteria, though they were far less widespread than they had been billions of years earlier in the Proterozoic eon. The Ordovician period ended dramatically. A series of extinctions swept through the oceans, wiping out enormous numbers of living organisms. Together, these events form the second largest mass extinction in Earth's history, surpassed only by the much later Permian Triassic extinction. These catastrophic events occurred between 447 and 444 million years ago, at the boundary between the Ordovician and the following Silurian period. At that time, all complex life still lived in the sea. Nearly half, about 49% of all animal genera disappeared forever. Brachiopods and bryozoans suffered especially heavily. Many species of trilobites, conodonts, and graptolites vanished. Most scientists link these extinctions to a sharp shift toward a colder global climate. The warm, stable greenhouse world of the Ordovician gave way to an ice age that began in the late Cation and peaked in the Hernantian. Glaciers expanded and global temperatures plummeted. This ice age may have lasted only 500,000 to 1.5 million years. However, some research suggests cool conditions didn't fully disappear until well into the Silurian period.
One major cause of Earth's cooling was a sharp drop in atmospheric carbon dioxide. During the Ordovician, its concentration may have fallen from around 7,000 to 4,400 parts per million. One possible cause was increased volcanic activity, creating fresh silicate rocks. As these rocks weathered, they absorbed carbon dioxide from the air. Another hypothesis links the cooling to the appearance of mosses, liverworts, and lichens on land, which intensified chemical weathering and also extracted carbon dioxide from the atmosphere. When carbon dioxide levels dropped, the greenhouse effect weakened, and Earth began cooling, especially in shallow seas where most marine life thrived.
There's an intriguing hypothesis that during the Ordovician, a ring system may have encircled Earth. Such rings could have partially blocked sunlight and contributed to cooling. A major meteor event from this time might also have affected the climate. As the southern supercontinent Gondwana drifted toward the South Pole, massive ice sheets formed on it. Glacial traces in upper Ordovician rocks from North Africa and parts of what is now northeastern South America support this, as these regions were near the South Pole then. As glaciers expanded, sea levels plummeted. Shallow inland seas once teeming with life retreated, destroying countless marine habitats. When seas briefly returned, they brought back fewer and less diverse communities. Then, new waves of glaciation forced the seas to retreat again, triggering more extinctions. This cycle of advance and retreat devastated shallow sea life, with species confined to isolated inland basins being especially vulnerable. The first extinction wave mainly hit tropical species, while the second affected cold water organisms more severely. Despite the catastrophe, some life forms adapted. During the coldest phase, deep ocean waters became oxygen-rich, allowing new bottom-dwelling organisms called the Hernantian fauna to spread widely across many parts of the world. Eventually, the Ice Age ended. As glaciers melted, sea levels rose and remained high for a long time. The flooding of continental shelves sparked a surge of new life. Many surviving groups rapidly diversified, filling ecological niches left by extinct species. Interestingly, some species that disappeared during the extinction later reappear in the fossil record. Scientists call these Lazarus taxa, as if they returned from the dead. These organisms likely survived the crisis in small, hidden refuges, waiting out the worst changes. One alternative hypothesis suggests Earth may have been struck by a powerful cosmic gamma-ray burst lasting just 10 seconds. It could have destroyed the ozone layer, exposed surface life to deadly ultraviolet radiation, caused mass die-offs, and possibly triggered cooling trends. More recent research suggests the late Ordovician extinction may not have been two separate events, but a single, prolonged crisis lasting several 100,000 years, with dramatic sea level and sediment changes causing successive waves of extinctions. The Silurian period was a remarkable chapter in Earth's history. Lasting about 23.5 million years, it began after the Ordovician, roughly 443 million years ago, and ended with the start of the Devonian, around 420 million years ago. It was the third of 6 major periods in the Paleozoic era, and the third of 12 periods in the Phanerozoic eon, the time of flourishing complex life on Earth. The Silurian began right after a devastating global catastrophe, one of the largest mass extinctions in Earth's oceans. During this crisis, around 60% of marine species disappeared. This marked a sharp turning point and a fresh start for life on our planet. One of the most important features of the Silurian is that life seriously began colonizing land. This great transition is often called the Silurian-Devonian terrestrial revolution. Before this, most life remained underwater, but now plants and animals started adapting to existence on land. Early land plants without roots or vascular tissue gradually gave rise to vascular plants, capable of transporting water and nutrients within their bodies and growing taller. Alongside them, new groups of fungi spread and diversified, especially helping plants form root systems and survive in harsh terrestrial environments. At the same time, 3 important groups of arthropods, millipedes, arachnids, and hexapods, meaning insects and their relatives, fully adapted to life on land. This was the first wave of animals to permanently leave the ocean. The Silurian also became a time of explosive growth in jawed fish diversity. New groups appeared: placoderms, the armored fish, acamphodians, from which modern sharks and rays descended, and osteichthyons, the bony fish. Later, bony fish split into two major lines: lobe-finned fish, which eventually gave rise to amphibians and humans, and ray-finned fish, which dominate the seas today. But while jawed fish flourished, more ancient jawless forms began to decline. The balance of power in the ocean was shifting. Scottish geologist Roderick Murchison first identified and described the Silurian period in the early 1830s. He studied the fossil-rich layers of South Wales and named the period after the Silures, an ancient Celtic tribe that lived in that region. His friend and colleague Adam Sedgwick, who had earlier named the Cambrian, inspired this choice. However, some rocks Murchison assigned to the Silurian overlapped with rocks Sedgwick assigned to the Cambrian. This sparked fierce scientific rivalry and ended their friendship. Eventually, English geologist Charles Lapworth resolved the dispute by establishing a new period between the Cambrian and Silurian, the Ordovician. In some countries, the Silurian was called the Gotlandian, after the rocks of Gotland Island in the Baltic Sea. French geologist Joachim Barrand, building on Murchison's work, divided the Silurian rocks of Bohemia, in what is now the Czech Republic, into 8 stages, though it later turned out that some of them actually belonged to the Devonian. Nevertheless, his research made Bohemia one of the most important regions for studying early Silurian fossils. In the Silurian, the ancient supercontinent Gondwana crossed the equator and occupied a significant part of the southern hemisphere. Meanwhile, the ocean covered the northern half of the planet. Because of very high sea levels and predominantly low, flat terrain, many small islands emerged, creating diverse conditions for life. Gondwana continued drifting slowly southward, but the ice caps left over from the previous period began to melt. As a result, sea levels rose. In many places, Silurian layers lie directly on eroded Ordovician rocks, showing geologists that the sea had flooded the land once again. The continents of Avalonia, Baltica, and Laurentia drifted toward the equator and eventually collided, beginning the formation of the supercontinent Euramerica. When Proto-Europe crashed into North America, millions of years of ancient sediments were compressed and folded. This massive geological event is known as the Caledonian Orogeny, a mountain-building episode that stretched from what is now New York State through Greenland and Europe to Norway. By the end of the Silurian, sea levels dropped again, leaving behind salty basins and evaporite deposits from Michigan to West Virginia. The newly formed mountain ranges eroded rapidly as ancient rivers carved through older Ordovician rocks, depositing Silurian sediments across present-day northern Ohio and Indiana. The northern hemisphere was dominated by the vast Panthalassa Ocean. Other ancient oceans existed too. Early versions of Tethys, including Proto-Tethys and Paleotethys, the Rheic Ocean, Iapetus, the Usk Sea between Avalonia and Laurentia, and the newly formed Euralian Ocean. Scientists once thought the Silurian was a time of calm, steady warmth, contrasting with the icy Ordovician before it and the scorching Devonian after. But we now know Silurian climate was anything but stable. The planet experienced numerous sharp climate shifts, evidenced by major changes in carbon and oxygen isotope ratios preserved in rocks from that era. Sea levels fluctuated dramatically. After rising from the Hernantian glaciation minimum at the period's start, they gradually fell again toward the end. But this wasn't a simple rise and fall. 15 separate episodes of high sea stands occurred when the ocean flooded the continental margins. At maximum, Silurian sea levels likely reached about 140 meters higher than the minimum. Earth entered a warm greenhouse phase. The atmosphere contained around 4,500 parts per million of carbon dioxide, far more than today. Warm, shallow seas spread widely across tropical regions. Early Silurian glaciers that once extended far across the continents shrank and retreated toward the South Pole, nearly vanishing by mid-period. The climate also featured powerful, frequent storms, evidenced by thick beds of shell hash created by storm waves battering the seafloor. Silurian climate and the carbon cycle proved surprisingly unstable, with changes occurring more frequently than in any other geological period. Scientists identify several such events, including the Ordovician, Mulder, and Lau events. Each brought minor extinctions, sharp sea level fluctuations, and notable shifts in carbon isotope composition. Organisms living freely in open water, like plankton, suffered especially. Brachiopods, corals, and trilobites were also hit hard. These extinctions often unfolded rapidly in short, sharp pulses. Some researchers link these fluctuations to repeated glaciations, but few glacial deposits like tillites are known from the Middle and Late Silurian, leaving the hypothesis controversial. Paleontologists view the Silurian as a recovery period following the late Ordovician mass extinction, which had interrupted the steady rise in biodiversity that began in the Cambrian and continued through most of the Ordovician. But the Silurian wasn't just about recovery. It brought many new beginnings. For the first time in Earth's history, large fossils of terrestrial life appeared. Among them were small moss-like plants growing along lakes and streams, forming the first primitive plant communities. There were also large fungal organisms, not plants, that formed networks and were likely closely associated with underground fungi. This marked the beginning of the Silurian-Devonian terrestrial revolution, as life gradually colonized the land. However, these early land organisms didn't yet have a major planetary impact. That came later in the Devonian. In the second half of the Silurian, something truly significant happened. The first vascular plants appeared, landforms with internal systems for transporting water and nutrients, a major evolutionary leap. The oldest known vascular plant was Chicxulub, a tiny plant growing along streams and rivers. Though its remains are found mainly in marine deposits, it most likely lived right at the water's edge. Around the same time, about 420 million years ago, during the Ludlow epoch, Barraguanathia appeared with needle-like leaves and branching stems. Barraguanathia fossils have been found in Australia, Canada, and China, showing remarkably complex structure for such an early plant. Another early land organism, possibly a plant, was Eohostimella, known from early Silurian impressions from the Landovery epoch. Its chemical composition is closer to vascular plants than algae, suggesting a terrestrial lifestyle. The Silurian also saw the earliest known land animals. Fossils about 425 million years old from Carrera Island include millipedes like Cambrian and Archidesmus. Other finds from the Ludlow epoch, about 420 million years old, include millipedes, centipedes, and arachnid trigonotarbids.
These animals show that simple food chains were already forming on land, with predators feeding on smaller creatures. In 1990, a team led by Andrew Jerram suggested that land animals, including tiny herbivores and decomposers, were far more numerous than the fossil record shows. Fossils from the Cowie Formation, including Cowiedesmus and Pneumodesmus, were once dated to the Middle Silurian, around 428 to 430 million years ago, but later research indicated these rocks might be early Devonian. Still, Pneumodesmus remains extremely important because it possesses the oldest known spiracles, breathing holes in a land animal. Underwater, life flourished again. The first bony fish, osteichthyons, appeared in the Silurian. One group, the acanthodians, was covered in small bony scales. Fish diversified and for the first time acquired movable jaws, which evolved from the front gill arches. Silurian seas, especially across what is now North America, were home to eurypterids or sea scorpions. Some reached several meters in length and dominated shallow waters. Brachiopods, marine animals with hard shells, remained extremely abundant. Many survived the Ordovician extinction and adapted to harsh conditions. Initially, certain groups were confined to single regions, but later spread widely again. The most successful brachiopods were orthids and pentamerids. Orthids recovered quickly, while pentamerids needed more time, showing significant growth only in the Aaronian age. Other marine animals thrived. Bryozoans, forming colonies, were often restricted to specific regions and formed symbiotic relationships with corals and stromatolites. Bivalve mollusks were common and began burrowing deeper into seafloor sediment for the first time. Chitons, armored marine mollusks, reached peak diversity in the Middle Silurian. Hydrozoans, unusual colonial organisms, entered symbiosis with certain corals like heliolites. The Silurian also became a golden age for tentaculatoids, mysterious small tubular marine creatures. They flourished especially in Baltica, Scandinavia, and spread widely during the Llandovery and Wenlock epochs. Even trilobites, the famous marine arthropods, experienced renewed success. Though their diversity declined after the Ordovician extinction, they still prospered in the Silurian, particularly in the Rudanian age. New crinoids, or sea lilies, appeared. Groups like flexibles, barely affected by the extinction, became more common. Monobathrid camerates diversified early, while eugeniocrines and dendrocrines expanded later. The unusual cyphocrinid group suddenly emerged near the Silurian's end and vanished just as quickly. Symbiosis was everywhere. Corals and stromatoporoid reef-building sponges often hosted endobiotic symbionts. Rugose corals were especially covered by epibionts, including the hydrozoans mentioned earlier. In the Middle Silurian, the first photosymbiotic scleractinians appeared, corals living in partnership with photosynthesizing organisms. Despite this richness, Silurian reefs are unevenly distributed in the fossil record. Some areas show abundant fossils, while others have almost none, leaving puzzling gaps. The Devonian period. One of the most fascinating chapters in Earth's long, dramatic history. It belongs to the Paleozoic era within the Phanerozoic eon, a vast time span when complex life apparently became commonplace. The Devonian lasted about 60,300,000 years. It began roughly 419 million years ago, after the Silurian, and ended around 359 million years ago, with the start of the Carboniferous period. It's the fourth geological period of the Paleozoic and Phanerozoic.
The name Devonian comes from Devon County in southwestern England, where rocks from this ancient time were first studied in detail. During the Devonian, Earth's surface underwent enormous changes, especially on land. Life, previously concentrated mainly in oceans, now began conquering continents. Vascular plants spreading spores through the air like ferns dispersed ever wider. Gradually they formed lush, dense forests that covered much of the land with a dark green blanket. By mid-Devonian, many plants developed true roots and broad leaves, and near the period's end, the first seed plants emerged, pteridosperms or seed ferns. This massive transformation of terrestrial life became part of the so-called Silurian-Devonian terrestrial revolution. This wasn't just the slow creep of mosses and roots. It was a drawn-out revolution that transformed the air, soil, and the entire face of the Earth. As plants evolved, the first land animals began to appear. These were mostly arthropods, invertebrates with jointed limbs and hard external skeletons. Among the pioneers were millipedes, spiders, and early insects, likely venturing onto land as far back as the Ordovician period. Meanwhile, beneath the waves, the oceans teemed with life, especially fish, whose diversity and numbers exploded. That's why the Devonian is often called the Age of Fishes. One group, the placoderms, wore thick armored plates and dominated many marine habitats. At the same time, cartilaginous fish, including primitive sharks, became more common than in the Silurian and late Ordovician. In Devonian freshwater ecosystems, a special group of fish emerged, the tetrapodomorphs. These became the ancestors of all four-limbed animals, including frogs, reptiles, birds, and humans. Their powerful, fleshy fins gradually transformed into limbs with hands and feet, though, according to the original text, they weren't yet ready for true walking on land. That transition came much later, in the late Carboniferous. The Devonian also saw the first ammonites, relatives of modern squid and octopuses with spiral shells and tentacles. Older marine animals like trilobites, brachiopods, and vast coral reefs still thrived, at least for a while. But then the Devonian story took a dark turn. Around 375 million years ago, the oceans suffered a devastating mass extinction. Many great reef systems collapsed. Jawless fish and placoderms nearly vanished, and only a small group of trilobites, the Proetida, survived. Another extinction followed soon after, around 359 million years ago, wiping out even more marine life, including calcite sponge reefs and the last placoderms. These two catastrophes barely ended the Age of Fishes and profoundly shook Earth's ecosystems. The Devonian world was shaped by three major landmasses. In the south lay the massive supercontinent Gondwana. To the north sat the smaller continent Siberia, and between them stretched the mid-sized landmass Laurussia. Major geological changes were underway. The ancient Rheic Ocean was closing. Southern China drifted from Gondwana, and a new ocean, Paleotethys, began opening. As continents drifted and collided, new mountain ranges rose. In North America, this led to the Akkadian orogeny, while in Europe, the Variscan orogeny began. These early mountain-building processes eventually led to the formation of Pangaea, the supercontinent that would dominate the late Paleozoic. The Devonian climate was generally warm, though at times, especially in the early and middle Devonian, glaciers may have existed. Unlike today, the temperature difference between the equator and poles was relatively small. Equatorial regions were particularly dry, and arid zones covered vast areas. Through microscopic fossils called conodonts, scientists estimate the average temperature of early Devonian tropical seas at around 30 degrees Celsius. The average surface temperature of the entire planet was probably around 16 degrees Celsius. One of the most important climatic changes of the Devonian was a significant drop in carbon dioxide concentration. The new forests spreading across land pulled carbon dioxide from the air and locked it in sediments. This triggered noticeable cooling during the Middle Devonian, when temperatures may have dropped by around 5 degrees Celsius. Later, in the Late Devonian, temperatures climbed back to roughly early Devonian levels. Interestingly, carbon dioxide concentrations didn't actually rise. Instead, warming likely resulted from increased continental weathering. Fossil plants also confirm a hotter Late Devonian climate. These temperature swings affected coral reefs too. During warm periods, microorganisms mainly built the reefs. In cooler times, corals and sponges dominated. But by the very end of the Devonian, the planet began cooling sharply again. This shift marked the start of the Late Paleozoic Ice Age, when massive ice sheets covered parts of the Earth. Throughout the Devonian, which began around 419 million years ago and ended roughly 359 million years ago, sea levels generally stayed quite high. The oceans then teemed with life, especially in shallow coastal waters. Many ancient marine organisms thrived during this era. Among them were tiny tooth-like conodonts, colonies of filter-feeding animals like bryozoans and brachiopods, superficially resembling modern clams, though actually a completely different group. There were also mysterious hydroids, tiny tubular microconchids, and various reef-building corals. Particularly abundant were graceful, flower-like crinoids, animals related to starfish. They looked like underwater flowers swaying in currents but actively captured food. Trilobites, once dominant in older seas, still existed but were no longer as widespread. Bivalve mollusks, ancestors of modern mussels, became common in deeper waters and outer continental shelf areas. One crucial early Devonian event, around 400 million years ago, was the appearance of the first ammonites, relatives of modern squid and octopuses with spiral shells. Around the same time, bactratoids first appeared. Both groups began spreading rapidly, possibly because deep ocean oxygen levels dropped. Older groups faced stress, while ecological niches opened for newcomers. Meanwhile, major changes swept the fish world. Ancient jawless fish covered in bony armor, known as ostracoderms, began declining. They were replaced by jawed fish, or gnathostomes, better adapted for hunting and defense. These jawed fish thrived in both seas and freshwater rivers and lakes. Among them were placoderms, heavily armored fish that dominated Devonian waters. However, by period's end, they went completely extinct, possibly unable to compete with faster, more efficient fish. Early representatives of modern shark and ray lineages, cartilaginous fish, appeared, along with bony fish. These groups became highly diverse and played vital roles in Devonian seas. One of the first well-known sharks, Cladocelashae, appeared during this time. Because of this explosive fish diversity, scientists often call the Devonian the Age of Fish. Simultaneously, thanks to abundant tiny plankton, free-swimming open-water organisms, the nekton, began rapidly multiplying and diversifying.
The ocean floor was already densely populated, so more and more animals began living and hunting in open water. This shift to active swimming is called the Devonian nekton revolution. However, not all scientists agree it was a true revolution. A study published in 2018 showed that while the proportion of nektonic species did increase between the Silurian and Devonian, it declined again during certain Devonian stages, especially in the Pangaean age. The authors noted that nekton diversity in the Devonian wasn't exceptionally high compared to earlier intervals like Wenlock to Lochkov, or later periods from Carboniferous to Permian. They argued that the rise of actively swimming animals wasn't a sudden leap, but part of a long, gradual trend spanning the entire Paleozoic. On Earth's surface, one of the most impressive structures of that time was a massive barrier reef in what is now the Canning Basin in northwestern Australia. It stretched approximately 350 kilometers.
Unlike modern reefs, built mainly by corals and algae, Devonian reefs formed differently. Some were microbial, composed largely of ancient photosynthesizing cyanobacteria. Others were coral stromatoporoid reefs, built by stromatoporoids together with tabulate and rugose corals. During the warm phases of the early and late Devonian, microbial reefs dominated, while in the cooler Middle Devonian, coral stromatoporoid reefs were more common. On land, changes were equally significant. By this time, Earth's surface was already partially green, thanks to mosses and algae that had spread during the Silurian. But in the early Devonian, more complex land plants appeared. They had simple roots, and through them, the first true soils began to form. Living nearby were tiny terrestrial animals, mites, scorpions, millipedes, including centipedes and diplopods, as well as trigonotarbids, thriving in this new green world. Ancient trace fossils suggest some of these animals may have lived on land even earlier, possibly as far back as the Cambrian. One of the strangest land organisms was Prototaxites, a giant creature reaching up to 8 meters tall. It looked like a tree trunk, but wasn't a plant. Some scientists think it was an enormous fungus, others a rolled mat of liverworts, or an entirely different organism. Insects may have appeared around this time too. Among early Devonian fossils, about 416 million years old, are remains that might belong to early insects. The emergence of vertebrates onto land is evidenced by Middle Devonian trace fossils linked to early tetrapods, the first four-legged animals and future ancestors of amphibians, reptiles, and mammals. However, some researchers believe these tracks could have been made by fish digging in sediment for food, rather than true land animals. Most of the earliest Devonian land plants were small, lacked true leaves, and reproduced by spores or vegetatively. Plants like Drepanoficus grew this way. One of the most ancient known forms, Cooksonia, reached only a few centimeters and had simple branching stems with sporangia at the tips. The major breakthrough came in the Middle Devonian, when plants with woody tissue appeared. Fossils from Armorica and Chateauneuf, about 400 million years old, contain the earliest evidence of wood. True trees emerged, including early lycophytes and tall cladoxylopsids and Archaeopteris, which were progymnosperms. These plants had real leaves and roots, and sturdy lignin in their tissues let them grow tall and better resist disease and herbivores. Some of Earth's first true forests appeared in the Eifelian age, dominated by cladoxylopsid trees.
By the end of the Devonian, seed-reproducing plants began to develop. The rapid evolution and spread of plant groups during this time is often called the Devonian explosion, or the terrestrial Devonian revolution. All this vegetation had another powerful impact. It pulled carbon dioxide from the atmosphere, contributing to global cooling and possibly to a major extinction event as environments changed too quickly for many species. As late Devonian plants with stems, leaves, and roots grew more complex and covered more land, ancient arthropods evolved alongside them. These animals, including early ancestors of insects, spiders, and crustaceans, gradually adapted to land, finding shelter and food in the expanding forests. Another important process began. Insects and seed plants started forming close relationships, an early partnership that eventually shaped modern ecosystems where bees pollinate flowers and plants use animals to spread seeds. Plants spread, roots penetrated deeper into the ground, soils formed, and wind and water began reshaping the land surface differently. Erosion and sediment patterns in rivers and oceans changed. As land stabilized and filled with plants and crawling animals, vertebrates began exploring terrestrial environments more actively. By the end of the Devonian, arthropods were firmly established on land. But even during this flourishing of life on land and in the sea, Earth was approaching one of its greatest extinction crises. The late Devonian extinction wasn't a single event, but a series of powerful pulses stretched over millions of years, hitting three key boundaries: Gevitian-Frasnian, Frasnian-Furmenian, and Devonian Carboniferous. Together, these events rank among the 5 great mass extinctions in Earth's history. The crisis hit ocean life hardest, especially warm, shallow water dwellers. Cool water species fared better. Reef builders, who had created some of Earth's largest and most spectacular reef systems, nearly vanished completely. Brachiopods, trilobites, ammonites, and acritarchs declined sharply. Conodonts and bony fish lost about 96% of their species. Even worse, ostracoderms, armored jawless fish, and placoderms, heavily armored jawed fish, disappeared entirely from the oceans. Surprisingly, terrestrial life suffered far less. Plants and freshwater animals, including early tetrapods, 4-legged ancestors of amphibians and reptiles, survived the crisis. Scientists believe early tetrapods might have also faced extinction, though evidence remains debated. The true cause of the late Devonian extinction is still unsolved. Many hypotheses exist, including Canadian paleontologist Digby McLaren's 1969 asteroid impact theory. While late Devonian impact evidence exists, like the Alamo structure, no crater large enough to explain such catastrophe has been found. The Carboniferous period was a crucial chapter in Earth's history, lasting about 60 million years. It began roughly 358 million years ago, after the Devonian, and ended around 298 million years ago with the Permian period. By the Carboniferous, land life had firmly established itself. Tetrapods, 4-limbed vertebrates descended from lobe-finned fish, now had 5 digits per limb. Amphibians were so numerous, this became known as the Age of Amphibians, with temnospondylus dominating among vertebrates. More significantly, amniotes emerged, land animals capable of laying eggs on dry ground. They split into synapsids, eventually leading to mammals, and sauropsids, ancestors of modern reptiles and birds. Meanwhile, land arthropods exploded in diversity.
giant scorpions, spider-like creatures, enormous millipedes like Arthropleura, and especially insects, including the first flying forms. Towering forests of giant ferns, seed ferns, and club mosses covered vast swamplands. Over millions of years, this vegetation buried and transformed into massive coal deposits, giving the period its name. In the second half, Earth entered a cooling phase, with glaciers forming in the southern hemisphere. Sea levels dropped as continents slowly converged into the supercontinent Pangaea. Near the period's end, a minor extinction event called the Carboniferous rainforest collapse occurred, when climate changes destroyed many rainforests. Long thought to be constantly high, atmospheric oxygen levels actually fluctuated significantly, starting low, then spiking to 25 to 30% compared to today's 21%. This high oxygen may have enabled some insects and arthropods to reach gigantic sizes. The idea of organizing Earth's layers into geological time emerged in the late 18th century. Irish geologist Richard Kirwan first used the term Carboniferous in 1799. The Carboniferous period was originally built from four main rock sequences: Old Red Sandstone, Carboniferous Limestone, Millstone Grit, and Coal Measures. In 1822, geologists William Conybeare and William Phillips formally combined these into a single subdivision. Then, in 1835, Phillips named it the Carboniferous system. Later, scientists discovered that Old Red Sandstone actually belonged to the older Devonian period. Since British rock layers closely resembled those in Western Europe, researchers created a unified European framework. They split the Carboniferous into two major divisions: the Lower Dinantian, dominated by limestones, and the Upper Silesian, composed mainly of sandstones and shales. The Dinantian was further divided into Tournaisian and Visean stages, while the Silesian was split into Nemurian, Westphalian, and Stephanian stages. In North America, geologists recognized a similar pattern, but chose to establish two separate systems: the Mississippian, rich in limestone, and the Pennsylvanian, rich in coal and shale. The United States Geological Survey officially adopted this division in 1953. In Russia during the 1840s, the Carboniferous was divided by local sections into Lower, Middle, and Upper series. By the 1890s, these became known as Dinantian, Moscovian, and Uralian. The Serpukovian stage was included in the Lower Carboniferous, while the Moscovian and Gazelian formed the upper part. Later, in 1934, the Bashkirian stage was added. In 1975, the International Commission on Stratigraphy officially standardized the Carboniferous scale, preserving the North American Mississippian and Pennsylvanian subsystems, the Western European Tournaisian and Visean stages, plus the Russian Serpukovian, Bashkirian, Moscovian, Kasimovian, and Gazelian stages. This made the older terms Dinantian and Silesian largely obsolete, though they're occasionally still used in Europe. To ensure geologists worldwide define time boundaries consistently, the International Commission on Stratigraphy uses global boundary stratotype sections and points, known as GSSPS. They select a specific rock layer at a specific location that officially marks the start of a stage. So far, only 3 Carboniferous stages have approved boundaries, as complex rocks and fossils are difficult to correlate globally. The name Mississippian was first proposed by Alexander Winchell in 1870, based on rocks from the upper Mississippi River. During this time, a shallow sea connected the Paleotethys Ocean with the vast Panthalassa, allowing marine organisms to spread widely, which made correlation by fossils easier. However, few volcanic rocks of Mississippian age are known, making precise dating difficult. The Tournasian stage, named after the Belgian town of Tournai, was established by André Dumont in 1832. The GSSP, marking the beginning of the Tournasian and the entire Carboniferous, is located in southern France at La Serre. Originally, the boundary was defined by the appearance of the fossil Siphonodella sulcata. Later research revealed problems with this criterion, complicating precise global correlation. The Visean stage, also introduced by Dumont in 1832, is named after the Belgian town of Visé. Its GSSP is now located in southern China and is defined by the appearance of Eoparistophila simplex, a tiny shelled organism. This decision was made in 2009. The Serpukovian stage was first proposed by Sergei Nikitin in 1890 and named after Serpukov near Moscow. It still has no officially approved GSSP. The boundary between the Visean and Serpukovian stages coincided with a significant cooling period and glacier expansion. Sea levels dropped, isolating many marine basins. Species in different regions began evolving separately, making it harder to correlate rock layers globally. Researchers are still searching the Urals and southern China for the best section to define this boundary, possibly using the first appearance of the conodont Lochria ziegleri. The Pennsylvanian subsystem takes its name from the American state of Pennsylvania, where thick, coal-bearing rock layers are widespread. Geologist J.J. Stevenson proposed this name back in 1888. During Pennsylvanian time, Earth underwent major changes. Most important was the closing of the Rake Ocean and the gradual assembly of continents into the supercontinent Pangaea. Meanwhile, large areas of the southern continent Gondwana were covered by massive ice sheets. The combination of continental movement and glaciation caused dramatic shifts in climate and sea level.
Marine animals became increasingly tied to specific regions, making it harder for scientists to correlate rock layers between different parts of the world. But Pangaea's formation also brought numerous volcanic eruptions. Volcanic layers can be dated more precisely using radiometric methods, so Pennsylvanian deposits are actually easier to study than earlier Mississippian ones. The first stage of the Pennsylvanian is the Bashkirian. Russian geologist Sofia Semikhatova established it in 1934. The name comes from Bashkiria, the former name for what is now the Republic of Bashkortostan in the southern Urals. The official start of the Pennsylvanian subsystem and Bashkirian stage is marked by the appearance of the tiny conodont Declinonathodus noduliferus. This boundary is fixed at Arrow Canyon in Nevada, United States, and was officially ratified in 1996. Back then, Arrow Canyon lay in a warm, shallow tropical sea stretching from Southern California to Alaska. The rock layers there form a repeating cyclothem sequence. Shallow marine limestones and sandstones alternate with mudstones and broken limestones, reflecting rises and falls of the ancient sea level. The Moscovian stage is named for marine limestones and multicolored clays around Moscow. Geologist Sergei Nikitin established it in 1890. This stage still lacks an officially ratified lower boundary. In northern and eastern Pangaea, a potential marker could be the tiny single-celled fusolinid Algutavella algutovica, but it occurs only in limited areas and doesn't work well for global correlation.
Other possible markers include the conodonts Declinognathodus donetzianus and Idiognathoides postsulcatus. Candidate sections for the official boundary include sites in the Urals and the Nishui area in Guizhou province, southwestern China. The Casimovian stage is the first stage of the Upper Pennsylvanian. It's named for the city of Kasimov in Russia and was initially part of Nikitin's Moscovian stage. Later, in 1926, Ape Ivanov separated it as an independent unit, naming it the Teguliferina horizon after a characteristic fossil brachiopod. The beginning of the Casimovian coincided with generally low global sea levels, creating many gaps in rocks of this age. This makes it difficult to find fossil species suitable for worldwide correlation. Like the Moscovian, the Casimovian stage still lacks an officially ratified boundary point. Scientists are considering several locations for reference sections: the southern Urals, the southwest United States, and Shui in China. The Gelian stage completes the Pennsylvanian. Named after the village of Gel near Ramenskoye in the Moscow region, it was identified by Sergei Nikitin back in 1890. It still lacks an official reference point. Fusulinids like Rauserites rossicus and Rauserites stukenbergi work well for dating rocks from the Boreal Sea and Paleotethys, but don't appear in eastern Pangaea or around the vast Panthalassa Ocean. Scientists are examining sections in the Urals and China's Guizhou province for more precise dating. The boundary between the Pennsylvanian and Permian periods is marked by a reference point in the Aydar-Alasha River Valley near Aktobe, Kazakhstan. Officially established in 1996, this boundary is identified by the first appearance of the conodont fossil Streptognathodus postfusus. A cyclothem is a repeating sequence of layers containing both marine sediments formed underwater and non-marine ones formed on land. Each cyclothem reflects one sedimentary cycle, beginning with an erosion surface. Individual cyclothems may be just a few meters thick, but their repeated stacking creates sequences hundreds or even thousands of meters deep. They formed on extremely shallow, gently sloping continental shelves, where even small sea level changes dramatically shifted coastlines, either flooding land or exposing large areas to erosion. Cyclothem formation peaked during the late Paleozoic Ice Age, lasting from the late Mississippian through the early Permian. When glaciers expanded, they pulled water from the ocean and sea levels dropped. Rivers carved channels into exposed land, while plant roots broke down rocks and built soil. These non-marine deposits formed each cyclothem's base. When glaciers melted, seas rose rapidly. Low-lying wetlands became peat bogs and swamps, where thick layers of plant matter accumulated in oxygen-poor conditions, eventually turning into coal. As seas advanced, these peatlands flooded and accumulated sediments from deltas, lagoons, and estuaries. Eventually, full marine conditions returned, depositing limestones and, at maximum sea levels, deep-water black shales. Sea levels then dropped again, but more slowly, so new deposits often didn't accumulate, and older layers eroded instead. Because sea level rise happened very quickly, the resulting sediment layers were typically less than 10 meters thick. During Pennsylvanian times, cyclothems were common in shallow tropical seas of La Russia, covering present-day western and central United States, Europe, Russia, and Central Asia, as well as the North China and South China cratons. These repeated sea level oscillations matched glacial cycles of the late Paleozoic Ice Age.
Each cycle followed roughly the 100,000-year Milankovitch rhythm that controlled Gondwanan glacier advances and retreats. Coal, the dark, energy-rich rock used as fuel, formed from layers of dead plant material accumulating in wet, oxygen-poor peat bogs. In these waterlogged places, plant remains piled up without fully decomposing. Over millions of years, thick, spongy peat layers were buried under heavy sediments, and pressure and heat gradually transformed them into coal. Most of the world's coal formed during a unique period in Earth's history, between the late Carboniferous and early Permian, roughly 323 to 285 million years ago. Plants in these ancient swamps not only turned into coal, but also changed the atmosphere by increasing oxygen levels. During Pennsylvanian time, enormous amounts of plant material accumulated in vast swampy lowlands near the equator. These lush lowlands stretched across the remains of central Pangaean mountains in ancient Laurussia and along the edges of what are now the North China and South China cratons. In the cold glacial periods, sea levels dropped, exposing wide areas of previously flooded land. Giant rivers, some several kilometers wide, cut through these new plains and fed smaller rivers, lakes, and peat bogs. When the earth warmed again and glaciers melted, the sea rose and buried the swampy areas under silt and sand. This cycle of exposure and burial repeated for millions of years, and the weight of new sediments gradually transformed the buried peat into thick coal seams. Scientists still debate why coal formation reached such massive scale specifically in the Carboniferous. One popular hypothesis suggests that trees had already learned to produce lignin, a decay-resistant compound in wood, but fungi capable of efficiently breaking down lignin hadn't yet evolved. So dead trees and plants simply accumulated in huge masses.
Genetic studies of basidiomycetes suggest the necessary lignin-degrading enzymes only appeared later in the Permian period. However, this idea remains controversial, as some evidence shows fungi could break down lignin by the end of the Devonian. Another hypothesis points to the unique geography and climate of the Carboniferous. Many continents were located near the equator, where it was hot and humid. The terrain was low, flat, and slowly subsiding, ideal conditions for endless swamps. Combined with extremely high plant productivity, this could explain the colossal accumulation of peat. All this occurred during the late Paleozoic glaciation, the longest and most intense glaciation of the last 540 million years. It began in the late Devonian around 365 million years ago and ended in the Permian approximately 253 million years ago. The main phase started around 335 million years ago and lasted until roughly 290 million years ago. As temperatures and carbon dioxide levels dropped, sea levels fell worldwide and massive ice centers formed on Gondwana, up to 30 separate zones covering parts of what is now eastern Australia, northwestern Argentina, southern Brazil, and southern Africa. Scientists believe this dramatic carbon dioxide decline was linked to the uplift of the central Pangaean mountains. As these mountains rose and eroded, rock weathering pulled carbon dioxide from the atmosphere. The closing of the seaway between the Rhyic Ocean and Tethys may have also intensified cooling by altering ocean currents and heat distribution across the planet. Despite the Ice Age, warming periods occurred. Warm intervals are recorded in the Bashkirian, late Muscovian, and from the late Casimovian to middle Gazelian times. When ice retreated, glacial deposits pulled back and sea levels rose again. In the early Casimovian, around 305 million years ago, Earth experienced a sudden, intense glaciation lasting less than 1 million years. During this brief cold snap, atmospheric carbon dioxide concentration plummeted to roughly 180 parts per million, below modern levels. But the cold ended just as abruptly when carbon dioxide surged to about 600 parts per million and the planet warmed. Such a spike could have been triggered by major volcanic eruptions or a slowdown in organic matter burial.
The coldest phase of the late Paleozoic glaciation occurred at the Carboniferous Permian boundary. Glacial traces from this time are found in South America, Africa, Antarctica, Australia, Tasmania, India, the Arabian Peninsula, and land blocks known as the Sumerian terranes, revealing the immense scale of ice sheets in the southern hemisphere. Simultaneously, carbon dioxide levels dropped again to approximately 175 parts per million and remained below 400 parts per million for the next 10 million years, largely because weathering of volcanic rocks continued absorbing carbon dioxide from the air. To understand the atmospheric composition of that era, scientists use several methods. Some data, like ancient gas bubbles trapped in halite crystals, provide snapshots of conditions. Other indicators, such as charcoal from ancient fires or minerals like pyrite, reveal broader trends. From the late Devonian onward, charcoal appears more frequently in the fossil record, indicating rising oxygen levels. Many scientists believe that for much of the Carboniferous, oxygen exceeded 21%. Gas bubbles in halite crystals aged 337 to 335 million years suggest oxygen may have been around 15% during Visian time, though this estimate is quite uncertain. Pyrite data show oxygen at roughly 15% in the early Carboniferous, rising above 25% during Pennsylvanian time, then dropping below 20% by period's end. While exact figures vary, all studies agree that from an initial 15 to 20%, oxygen climbed to a late Carboniferous peak of 25 to 30%. The rise was uneven. Oxygen levels fluctuated with climate shifts. Some researchers propose that high oxygen supported the giant insects and other large animals of the Carboniferous, though this hypothesis remains under investigation and debate. In the early and middle Mississippian, roughly 359 to 323 million years ago, the oceans stayed relatively warm. In these warm, shallow seas, carbonate rocks formed in massive quantities, primarily limestone. They spread widely across the gently sloping continental margins of Laurussia, which included parts of what are now North America and Europe, as well as the ancient landmasses of North and South China.
This geological setting resembled a carbonate ramp, a gently inclined underwater space where sediments gradually accumulated layer by layer. Along the coasts of Laurussia, Kazakhstan, and northern Gondwana, evaporation of shallow seas also created thick deposits of evaporites, including rock salt and gypsum. But when cooling began in the late Visian, around 330 million years ago, carbonate formation became restricted. In deep waters, it almost stopped entirely, concentrating mainly at depths less than 10 meters. This created broad, flat carbonate platforms with steep edges resembling modern underwater cliffs. By the Muscovian Age, which started around 315 million years ago, Earth's ice sheets cyclically expanded and contracted, creating distinctive sedimentary sequences called cyclothems. These cyclothems consisted of alternating carbonate and terrigenous layers, sand, silt, and other materials deposited on shelves and platforms during repeated sea level rises and falls. As Gondwana's glaciers grew and then melted, cold waters spread along its margins, lowering surrounding ocean temperatures nearly to freezing. Evidence of this comes from glendonites, a well-known mineral forming from echite, a variety of calcium carbonate that crystallizes only in cold water. Glendonites found in fine-grained marine sediments confirm the cold conditions of that era.
Glacial movement across Gondwana and the uplift of central Pangaean mountains ground down rocks, creating enormous volumes of fine silt material. Eventually, this dust-like fertile sediment spread across the equator, covering large areas of what would become central Pangaea and creating extensive loess deposits. Late Paleozoic glaciation was initially considered exclusively catastrophic for marine life. Many species did disappear, and overall biodiversity remained low for some time. But new research shows this wasn't just an era of losses. The sharp and extreme climate and environmental changes stimulated rapid evolution and the appearance of many new marine species, a phenomenon called adaptive radiation. The constantly changing climate repeatedly restructured the vast tropical forests of Laurussia, transforming them from swampy forests to dry seasonal ones and back again. During the Kazimovian glacial episode, which began around 307 million years ago, many tall tree-like ferns and other wetland plants declined or disappeared.
This biodiversity drop closely linked to a sharp fall in carbon dioxide concentration below 400 parts per million. Though the event is called the Carboniferous rainforest collapse, rainforests didn't vanish completely. One type of tropical forest ecosystem gradually gave way to another. When the Carboniferous yielded to the Permian around 299 million years ago, conditions became even drier, especially at low latitudes. Carbon dioxide levels dropped further still, and new forests adapted to seasonal drought. Around that time, tetrapods developed new traits that made land life easier, and amniotes, well adapted to dry climates, began spreading widely. Early Carboniferous land plants, some preserved in coal nodules, resembled those of the late Devonian, but new groups emerged. Major groups included horsetails, giant relatives of modern rushes, sphenophyllum vines, lycophytes, lepidodendrids, ferns, medullosan seed ferns, and cordytes, early relatives of conifers. These plants dominated Carboniferous landscapes. Later in the period, other groups appeared: cycads, calistophyte seed ferns, and voltziales, early conifers. Some Carboniferous lycophytes, especially lepidodendrids, bore no resemblance to today's small club mosses. These were giant trees, reaching 30 meters tall with trunks up to 1.5 meters thick, including Lepidodendron, Anabathra, Lepidophlorus, and Sigillaria. Their roots, known as stigmaria in the fossil record, formed dense underground networks. Unlike modern trees, their strength came from thick outer bark rather than inner xylem. Another ancient group, Cladoxylopsids, were tall plants from which true ferns later evolved. Many Carboniferous fern fronds so closely resemble modern ones that they're hard to distinguish. Some ancient ferns possibly even grew on other trees as epiphytes. Fossil records show numerous ferns and seed ferns: Pecopteris, Neuropteris, Alethopteris, and Sphenopteris, plus tree forms like Megaphyton and Ceronius. Among horsetails were giant calamites with hollow, jointed stems reaching 20 meters tall and 30 to 60 centimeters thick. Another vine, Sphenophyllum, had walls of narrow leaves and was likely related to both calamites and lycophytes. Tall cordytes with long strap-shaped leaves reached 6 to over 30 meters and are considered early relatives of cycads and conifers. They formed cone-like structures called chordaecarpon and probably thrived in swamps. True conifers, like Walkia from the Voltziales, appeared later in the Carboniferous and preferred drier highlands. Underwater life flourished too. Marine invertebrates showed great diversity: foraminifera,
corals, bryozoans, ostracods, brachiopods, ammonoids, hyalithids, microconchids, and crinoids. Brachiopods and fusolinid foraminifera became especially numerous during Mississippian times, though some groups like cephalopods and conodonts began declining. This surge in marine diversity is called the Carboniferous Early Permian Biodiversity Event. One of the most widespread successful foraminifera genera was Fusolina, inhabiting ancient seas across present-day Russia, China, Japan, and North America. Microscopic shelled organisms like radiolarians were found in siliceous rocks, cherts from the Devonian of Cornwall, England, as well as Russia and Germany. Sponges were common too, including groups like Chaetidids, Hindia, and the colonial glass sponge Hydmoceras. Coral reefs continued growing with diverse forms like Caninia, Dibunophyllum, and Michelinea. Especially numerous were fan-shaped phenestellid bryozoans, including the spiral Archimedes, plus Phenestella and Polypora. Brachiopods thrived during this period. The giant Gigantoproductus reached about 30 centimeters in width, while Chonatids were smaller and simpler in form. Aetheridids, Spiripherids, Rhynchonellids, and Terebratulids were also common. Some inarticulate brachiopods like Disconisca and Crania appeared as well. Worm-like annelids such as serpolites are found in many layers, and mollusks continued growing in number and diversity. Common bivalves included Aviculopecten, Posidonomia, and Carbonacula, along with gastropods like Murchisonia, Euomphalus, and Natocopsis. Orthoconautiloids became rarer, but tightly coiled nautilids and goniatite ammonoids like Anthracoceras remained widespread. Trilobites, once abundant, grew scarce and were mainly represented by protids. Small crustacean ostracods stayed common, including genera like Bairdia, Cavallina, and Healdia. Crinoids, or sea lilies, were especially numerous, sometimes forming dense underwater meadows whose remains created thick limestone beds after death. Common genera included Cyathocrinus, Woodocrinus, and Actinocrinus. Sea urchins like Archaeosideris and Polychinus also lived then.
Blastoids, resembling crinoids and anchored by long stems, reached their peak in the Carboniferous, including families like Pentramididae and Codisteridae, showing how rich and strange the underwater world was. For tens of millions of years, life both in water and on land displayed incredible richness and diversity. Freshwater bodies teemed with invertebrates. Among the most common inhabitants of fresh and brackish water were hard-shelled bivalves like Anthraconaea, Naiadites, and Carbonecula living in rivers and swamps. Many crustaceans with hard exoskeletons and jointed limbs existed, including Candona, Carbonida, Darwinula, Asteria, Acanthocaris, Dithyrocaris, and Anthropolemon. Another interesting group were Eurypterids, or sea scorpions, among the largest arthropods ever. Some, like Adelophthalmus, Megarachne, once mistakenly identified as a giant spider, and massive Hybertopterus, lived in shallow water and possibly made brief land excursions, likely being amphibious. Sometimes the sea briefly returned to these low, swampy areas, leaving thin sedimentary bands called marine bands, containing fossils of saltwater animals like Lingula, Orbiculoidea, and Productus. On land, many air-breathing arthropods appeared. Carboniferous rocks contain insects, millipedes, and arachnids, showing arthropods were already widespread and extremely diverse. Some reached enormous sizes. Among the largest was Arthropleura, a giant millipede-like creature up to 2.5 meters long, the largest known terrestrial invertebrate in Earth's history.
In the mid-Mississippian, the early part of the Carboniferous, the first winged insects appeared. Soon, huge predatory insects dominated the skies, protodontates or griffin flies. Among them was Meganeura, resembling a giant dragonfly with a wingspan of about 75 centimeters, one of the largest known flying insects. Other early groups included Syntenapterids, ancient relatives of mayflies, numerous and often large herbivorous paleodictyopteroids with piercing, sucking mouthparts, herbivorous protothopterans, and primitive cockroach ancestors, the dictyopterans. Many of these ancient insects were found in rich deposits of the Saarbrücken coal basin in Germany and Commentry in France, as well as inside fossilized hollow tree trunks in Nova Scotia, Canada. British coal basins also yielded well-preserved finds, such as Archaeopteryx, parts of whose large wings exceeded 4 centimeters.
Some insects, like the genus Brodia, preserved traces of bright pigment on their fossil wings. Interestingly, inside the hollow trunks of Nova Scotia, scientists also found early terrestrial snails, archaeozonites, and dendropupa. Meanwhile, Carboniferous seas teemed with fish, especially elasmobranchs, the group that includes sharks and rays. Some, like Sandilodes, had powerful flat teeth, perfect for crushing hard shells of brachiopods and crustacean carapaces. Others, like the Ctenacanthiforms, reached impressive sizes. Some forms, including Cyvides, could grow from roughly 6 to 9 meters. There were sharp-toothed groups too, like the Psammoriids and Petalodontids, with unusual cutting-tooth spirals. Most large predatory fish lived in the sea, but some, like the xenocanths, adapted to freshwater swamps of coal forests. Bandringa also penetrated into fresh inland waters. Among bony fish, paleoniscoids often lived along coasts but also moved upstream. The Sarcopterygians, or lobe-finned fish, included rhizodonts that reached large sizes and likely occupied the top of food chains. Much of our knowledge about Carboniferous marine fish comes from fossilized teeth, fin spines, and dermal armor fragments. Small freshwater fish, sometimes preserved whole, including Canobius, Uranotis, Acanthodes, Gyrocanthus, and others. During this time, cartilaginous fish experienced a notable evolutionary surge, especially holocephalans, relatives of modern chimeras. This burst likely began because after the extinction of armored placoderms at the end of the Devonian, numerous ecological niches opened up for new fish to occupy. One of the strangest holocephalans was Stethocanthus, a shark-like fish with an unusual, flat, brush-like dorsal fin covered in small, tooth-like scales, possibly used in mating displays. Another unusual group were the Eugeniodontids, which developed characteristic tooth whorls instead of normal tooth rows. These included helicoprionids, early Eugeniodontids that appeared in the early Carboniferous and became famous for their spiral dental apparatus in the lower jaw. Even stranger looking were certain holocephalan forms that somewhat resembled modern flying fish, with huge pectoral fins for gliding through water, large eyes, club-shaped tails, and sharp spines on fin tips. By mid-Carboniferous, amphibians on land were becoming increasingly numerous and diverse. There were far more of them, with much greater variety than modern amphibians. Some reached 6 meters in length. More advanced terrestrial forms developed scaly skin that helped retain moisture. Many early amphibians belonged to the labyrinthodonts, with long bodies, bony heads, and relatively weak limbs. Some grew to over 2 meters. Living alongside them were smaller lepispondals, often just 15 centimeters long. Certain amphibians, like Loxama, Eogyrinus, and Proterogyrinus, inhabited rivers and were fully aquatic.
Others, such as Aestopod, Amphibamus, and Hyloplesian, likely lived both in water and on land. Still others, including Dendroepiton, Tuditanus, and Anthracosaur, may have spent most of their lives on land. But as the Carboniferous drew to a close, the vast tropical forests began to collapse, probably due to a shift toward cooler, drier conditions. For amphibians dependent on moisture for survival and reproduction, these changes proved devastating. Amniotes, however, a new vertebrate group including early reptiles and synapsids, began to flourish thanks to crucial evolutionary advantages. They laid shelled eggs that could develop on land. Waterproof, scaly skin and claws made terrestrial life easier. Among the earliest reptiles was Hylonomus, while the first known synapsid is Archaeothyrus. Synapsids would later give rise to mammals, rapidly increasing in size and diversity during the Permian before losing dominance in the Mesozoic. Reptiles, especially sauropsids, remained small initially, but later dominated land, sea, and air during the age of dinosaurs, maintaining that supremacy until their decline in the Cenozoic. As the climate dried at the Carboniferous's end, reptiles spread and diversified rapidly. By then, amniotes had split into several groups including pelycosaurs, early synapsids, protorothyridids, captorhinids, Areoscalidians, and diapsids, each opening a separate evolutionary pathway. While plants and animals thrived and grew larger, fungi diversified actively, especially on land. Marine fungi continued in the oceans, and by the late Carboniferous, nearly all modern fungal classes had appeared on land. The first 15 million years of the Carboniferous left extremely few terrestrial fossils. Scientists have long debated whether this gap reflects poor preservation conditions or something genuinely catastrophic. Recent research points to a significant drop in atmospheric oxygen at this time, suggesting a major ecological crisis or even partial collapse of terrestrial ecosystems.
Through these changes, some ancient groups vanished, including the ichthyostigalians, fish-like early amphibians of the Devonian, whose bodies still resembled fish, though they were beginning to colonize land. Gradually, they were replaced by more advanced amphibians. Two important groups came to dominate: the large and diverse temnospondylus and the reptiliomorphs, which were closer to true reptiles. During the Carboniferous, these new forms became the most common land vertebrates. But near the period's end, Earth faced another major extinction known as the Carboniferous rainforest collapse. The vast rainforests that once covered endless territories began disintegrating rapidly. Earth's climate, previously hot and humid and ideal for lush jungles, became cooler and much drier. This sharp shift is believed connected to massive glaciation, the formation of enormous ice sheets, and a severe drop in global sea levels. As the environment dried, the tropical forests could no longer sustain themselves. They fragmented into isolated patches like green islands scattered across arid land. The vast forests of giant lycophytes, ancient relatives of today's club mosses, gradually gave way to simpler woodlands dominated by tree ferns and far less diverse. The sudden climate shift hit amphibians especially hard. These animals, then the most common land vertebrates, struggled to survive in the new conditions. Many species vanished and amphibian diversity plummeted. Reptiles, however, began to thrive. They possessed key traits that gave them an edge in the drier, harsher world. Reptiles laid eggs with tough shells that resisted drying out, and their scaly skin helped retain moisture. With these adaptations, reptiles spread and flourished while their amphibian cousins declined. The Permian period was a pivotal chapter in Earth's ancient history. It lasted roughly 47 million years
beginning after the Carboniferous around 298,900,000 years ago and ending with the start of the Triassic about 251,900,000 years ago. The Permian was the sixth and final period of the Paleozoic era, after which the Mesozoic began with the Triassic. The name Permian was first used in 1841 by British geologist Sir Roderick Murchison.
He named the period after the Russian region of Perm, where he and French geologist Édouard de Verneuil discovered a characteristic sequence of rock layers during their studies of the Ural Mountains. There, Murchison observed a massive succession of different rocks, marls, limestones, shales, sandstones, and conglomerates, lying above older Carboniferous deposits. These layers resembled nothing previously described, and the Permian was recognized as a distinct geological period. During the Permian, Earth looked completely different. All continents merged into one enormous supercontinent called Pangaea, which formed after the collision of Euramerica and Gondwana back in the Carboniferous. A giant global ocean, Panthalassa, surrounded Pangaea. Inside the supercontinent, the climate grew hotter and drier, especially after the collapse of the Carboniferous forests left vast stretches of arid desert. As conditions grew harsher, animals had to adapt. Amphibians, which needed water for life and reproduction, began to retreat. Their place was taken by amniotes, animals that laid shell-protected eggs and were therefore far better suited to dry environments. Over time, amniotes split into two major lineages: synapsids, which included the ancestors of mammals, and sauropsids, which encompass reptiles and eventually birds. The Permian period was also marked by several waves of extinction, at least 3 and possibly 4 by various estimates. One major extinction occurred at the end of the early Permian, during the Ciceralian epoch. During this crisis, many early synapsids disappeared, especially the so-called pelycosaurs, while more advanced therapsids began to take center stage. Later, in the Capetanian age, near the end of the Middle Permian, another major extinction struck, likely linked to massive volcanism in what is now China that formed the Emerson Traps. But the greatest catastrophe was still to come. Around 251 million years ago, at the very end of the Permian, Earth experienced its most devastating mass extinction. The Permian Triassic extinction, sometimes called the Great Dying, wiped out roughly 81% of marine species and 70% of terrestrial species. This global catastrophe is closely linked to massive volcanic eruptions in Siberia that formed the Siberian Traps. Enormous volumes of lava and ash released toxic gases and carbon dioxide, triggering climate collapse.
Recovery took an incredibly long time. Terrestrial ecosystems needed about 30 million years of the Triassic period to fully rebound. Even the Permian's name sparked controversy. Between 1853 and 1867, Franco-American geologist Jules Marcoux found Permian rocks across a vast stretch of North America, from the Mississippi to the Colorado River. He proposed calling the period Dacian, combining parts of two words. But Murchison strongly objected, and the name never caught on. For many years, the United States Geological Survey refused to recognize the Permian as a separate period, treating it as part of the Carboniferous alongside the Mississippian and Pennsylvanian subdivisions until 1941. Today, the Permian is divided into 3 major epochs, from oldest to youngest: Ciceralian, Guadalupian, and Lopingian. Each breaks down into smaller intervals called stages,
which correspond to rock layers in different parts of the world and help date rocks across continents. For precise global correlation, the International Commission on Stratigraphy uses Global Stratotype Sections and Points, GSSPS. These are specific locations, usually geological outcrops, that officially mark the beginning of a stage and serve as reference points for geologists worldwide. For most of the 20th century, the Permian was split into only early and late epochs, with the Cambrian stage considered the last stage of the early Permian. But in 1992, geologist Glenister and colleagues proposed grouping the Rhodian through Capetanian stages into a separate middle epoch. This was officially adopted in 1999, making the threefold division standard. Earlier studies of marine Permian rocks relied mainly on ammonoids, spiral-shelled relatives of modern squid and octopuses. But ammonoids are relatively rare in Permian strata, and individual species often persisted for millions of years, making them poor markers for short time intervals. So today, key Permian boundaries are more often defined by the remains of another ancient group, conodonts. Conodonts were mysterious, eel-like, jawless animals with tiny tooth-like elements in their feeding apparatus. Though long extinct, their hard oral structures preserve well and occur in many Paleozoic and Triassic layers, making them ideal for dating and correlating rocks worldwide. Official GSSPs marking the start of each Permian stage are now based on the first appearance of specific conodont species. The Cicxulub series, the earliest part of the Permian, is named after rocks on the western slopes of the Ural Mountains in modern-day Russia and Kazakhstan. Geologist J.B. Waterhouse proposed the term Cicxulub in 1982. It originally included three stages, Aselian, Sackmerian, and Artinskian, but the Cambrian was later added to align the international scheme with the Russian classification of the Lower Permian. In 1900, French geologist Albert-Auguste Cochon de la Parent proposed the term Uralian series, but it was abandoned due to inconsistent usage. The Aselian stage was named in 1954 by Russian geologist 5E. Ruzhentsev for the southern Urals. The official GSSP marking the base of the Aselian is located in the Adaralasha River Valley near Aktobe in Kazakhstan. This boundary was ratified in 1996 and defined by the first appearance of the conodont Streptognathodus postfusus. The Sackmerian stage takes its name from the Sakhmara River in the southern Urals. It was introduced by renowned Russian geologist Alexander Karpinsky in 1874. The GSSP for the base of the Sackmerian lies in the Usolka section in the same region, with the boundary officially ratified in 2018. It's defined by the first appearance of the conodont Sweetognathus binodosus. The Artinskian stage is named after the town of Arty in Sverdlovsk Oblast, Russia. Like the Sackmerian, it was established by Karpinsky in 1874. An official GSSP for the base of the Artinskian has not yet been ratified, though scientists have proposed defining it by the first appearance of the conodont Sweetognathus afflegasus marilli. The Cambrian stage is named after the town of Kungur in Perm Krai. It was introduced by Alexander Antonovich Stuckenberg in 1890. Like the Artinskian, it still lacks an officially ratified GSSP, though recent research suggests marking its base with the first appearance of the conodont Neostreptognathodus nevi. The Middle Permian comprises the Guadalupean series, named for the Guadalupe Mountains in Texas and New Mexico. The name was first used in 1902 by American paleontologist George Herbert Gertie, who studied the thick marine rock sequences of this region. The first stage of the Guadalupean is the Rhodian, named in 1968 for the Rhode Canyon member of the Word Formation in Texas. The GSSP for the base of the Rhodian is located in Stratotype Canyon in the Guadalupe Mountains, approximately 42.7 meters above the base of the Cutoff Formation. This GSSP was ratified in 2001, with the boundary defined by the first appearance of the conodont Gynogondylella nankingensis. The second stage is the Wordian, named after the Word Formation. In formal stratigraphic terms, Glenister and Furnish first used it in 1961, though Johann August Udden had proposed the name back in 1916. The GSSP for the Wordian is located at Guadalupe Pass, Texas, in the Getaway Limestone member of the Cherry Canyon Formation. This GSSP was also ratified in 2001, with the stage base defined by the first appearance of Gynogondylella acerata, another conodont species. The final stage of the Guadalupean is the Capitanian, named for the Capitan Reef in the Guadalupe Mountains. George Burr Richardson first proposed the name in 1904, and Glenister and Furnish used it as an official substage in 1961. In 2001, the International Commission on Stratigraphy officially recognized the Capitanian as an international stage. Its GSSP is located at Nipple Hill in the southeastern Guadalupe Mountains, with the base defined by the first appearance of the conodont Gynogondylella postserrata. The term Lopingian was first introduced in 1923 by geologist Amadeus William Grabau, naming the series after the city of Leping in China's Jiangxi province. Initially, it referred to a specific type of layer, a lithostratigraphic unit. But in 1932, Chinese geologist Ting-Ying Huang expanded its meaning, elevating Lopingian to series rank and including all Permian strata of South China lying above the Maoku limestone. Many years later, in 1995, the Subcommission on Permian Stratigraphy officially voted to recognize the Lopingian series as a global chronostratigraphic unit. This series contains two main stages, the Wuqiaopingian and the Changxingian. A geologist named Zhao Jingke first proposed these names in 1962, deriving them from the Wuqiaoping and Changxing formations within the Lopingian deposits. Scientists established the official boundary for the start of the Wuqiaopingian stage in 2004 at the Penglaitan section in Guangxi, China. It's marked by the first appearance of a tiny tooth-like fossil of the conodont Clarkina postbitteri, a member of a mysterious group of extinct jawless creatures. The Changxingian stage takes its name from the Changxing limestones, first described by Grabau back in 1923. These limestones are named after Changxing County in Zhejiang Province. The boundary marking the beginning of the Changxingian sits about 88 centimeters above the base of the Changxing limestones in the Meishan D section in Zhejiang. This boundary was officially ratified in 2005 and is defined by the first appearance of another conodont, Clarkina wongi. For the boundary between the Permian and Triassic periods, scientists chose the base of bed 27C in that same Meishan D section. This point became the official boundary in 2001, marked by the first appearance of yet another conodont, Hindiotis parvis. In the traditional Russian stratigraphic school, there's a Tatarian stage that spans the entire Lopingian as well as the earlier Capitanian and part of the Wordian stages. Below that sits the Kazanian stage, which includes the rest of the Wordian and the even earlier Rhodian stage.
In North America, the earliest division is the Wolfcampian, containing the smaller Nelian and Lennoxian stages. Next comes the Leonardian with its Hessian and Cathedral stages, followed by the Guadalupian, and then the Ochoan, which roughly corresponds to the Lopingian elsewhere. New Zealand developed its own three-part Permian scale. The earliest, the Pre-Tettlefordian, has no further subdivisions and roughly matches the Acelian, Sacmarian, and Artinskian stages. Then comes the Dervillian epoch, divided into the Macarewan, Wattian, and Purahawan stages, corresponding approximately to the Kungurian stage and Guadalupian epoch. The final Aparaman epoch includes the Fletcher, Barrett, Mongoparan, and Tettlefordian stages, closely matching the Lopingian epoch. By the Permian period, all of Earth's major land masses had united into a single gigantic supercontinent called Pangaea. To Pangaea's east lay smaller continental fragments known as the Cretaceous terranes. This enormous landmass stretched from near the equator almost to the poles, profoundly influencing global climate and ocean currents.
Surrounding the supercontinent was the vast Panthalassa, whose name means universal sea. Between Asia and southern Gondwana lay the smaller Paleotethys Ocean. During this time, a smaller continent called Cimmeria split off from Gondwana and began drifting northward toward Laurasia, gradually narrowing the Paleotethys. Meanwhile, in the south, a new ocean called Neotethys began to open, destined to become one of the major oceans of the Mesozoic era. As the oceanic plate of Panthalassa subducted beneath the southeastern margin of South China, it created a volcanic chain, a magmatic arc stretching to Hainan Island. The central Pangaean mountains had begun forming back in the Carboniferous when Laurasia and Gondwana collided. They reached their greatest heights in the early Permian, roughly 295 million years ago, and are thought to have rivaled today's Himalayas. Over time, erosion wore them down. Elsewhere, the Kazakhstania block collided with Baltica during the early Permian in the Ciceralian epoch. By the end of the Permian, several land masses, including the North China Craton, South China Block, and Indochina, had joined together and become part of Pangaea. In what is now northwestern Europe, there existed the salty inland Zechstein Sea, an extremely saline epicontinental body of water. The interior regions of the vast supercontinent Pangaea lay far from the moderating influence of the ocean and experienced extreme temperature swings, scorching summers and freezing winters. Additionally, rainy seasons alternated with dry spells, much like modern monsoons. Deserts covered vast stretches of Pangaea. The arid environment favored gymnosperms such as conifers, cycads, and ginkgos, which tolerate drought better than ferns, which need moisture to reproduce. It was during this time that the first modern-type trees appeared. Among the most important regions in the world for studying Permian rocks are the Ural Mountains in Russia, from which the period takes its name, areas of China, and the American Southwest, particularly Texas, with its vivid red layers known as the Texas Redbeds. The Permian Basin, spanning Texas and New Mexico, is named for its thick sequences of Permian strata and contains some of the most extensive Permian deposits on Earth. At the very beginning of the Permian, in the Acelian Age, sea level dropped slightly. Throughout most of the early Permian, it remained relatively high, several tens of meters above present levels. But starting in the Rhodian Age, it began to fall sharply. The lowest point came during the Wuchiapingian Age, when sea level approached modern values. Afterward, in the Chongqingian Age, the sea rose slightly again. In the early Permian, Earth was still in an ice age that had begun in the late Devonian, over 360 million years ago, and lasted throughout the Carboniferous.
Its coldest phase was the late Pennsylvanian, part of the Carboniferous period. With the start of the Permian, the climate gradually shifted. During the Ciceralian epoch, which makes up the early Permian, the planet became increasingly dry. Drying was especially pronounced at the equator, particularly across vast Pangaea. At the same time, melting of ancient glaciers raised sea levels. At the boundary between the Carboniferous and Permian, a brief warming occurred. Despite rising temperatures, the climate became significantly drier and arid conditions persisted. However, in the Acelian and Sacmarian ages of the early Permian, Earth cooled again, reaching the peak of the Ice Age. Then, around 287 million years ago, abrupt Artinskian warming began and the climate warmed once more. The massive ice cap at the South Pole started to retreat, though isolated glaciers remained in the highlands of eastern Australia, northern Siberia, and southern Africa. The warming was accompanied by even more intense drought, especially in the continental interiors. Later, near the end of the Kungurian Age, Earth cooled again and a new glacial phase began, lasting into the early Capetanian Age. Though the climate became cooler, average temperatures still remained higher than at the very beginning of the Permian. In the Middle Capetanian Age, another cooling event occurred, lasting about 3 to 4 million years, known as the Kimura event. But this cool phase did not last long. Around 260 million years ago, massive eruptions in what is now southwestern China created the Imishan traps. The gases and heat from these eruptions triggered sudden warming, the Imishan thermal excursion, which contributed to the Capetanian mass extinction. As the late Permian Wuchiapingian Age began, the remaining Imishan volcanic rocks started pulling carbon dioxide from the air, cooling the planet again. By late Wuchiapingian time, the long late Paleozoic Ice Age finally ended, and Australia's last glaciers melted.
But the most dramatic climate event lay ahead: the end of the Permian. At the Permian-Triassic boundary, colossal eruptions in Siberia formed the Siberian traps, releasing over 5 quadrillion tons of carbon dioxide and more than doubling atmospheric levels. This massive influx of greenhouse gases caused severe warming, recorded in sharp oxygen isotope shifts in ancient rocks. The consequences were catastrophic. The Permian-Triassic mass extinction became Earth's largest ever, devastating nearly all life. The planet entered an extreme greenhouse state that persisted for millions of years into the Triassic. Permian climate featured extreme seasonality. Pangaea's enormous size and position created a unique circulation system, a mega monsoon. These powerful seasonal winds brought severe drought to the supercontinent's interior, while drenching the western shores of the ancient Paleotethys Ocean. Scientists have found extensive evidence of this mega monsoon. Ancient rainforest traces in Tibet's Changtang Basin, and rocks from Queensland, Australia, showing strong seasonal patterns in rainfall, burrows, and fossil composition. Climate models based on atmospheric physics confirm that such a powerful monsoon system would naturally arise under Permian conditions. Permian oceans teemed with life: mollusks, brachiopods, echinoderms, sea stars, and urchins. Brachiopods were especially numerous and diverse. Productids made up roughly half of all known brachiopod genera, and even shaped reef ecosystems. Among shelled ammonoids, goniatids were common in the early and middle Permian, but later declined. Proleconitis never achieved great diversity, but in the middle Permian, they gave rise to ceratitids, which spread rapidly by period's end. Only 3 trilobite families survived into the Permian: protids, brachiotopids, and philopseids. They changed little at first, but from the Cambrian to Wordian experienced a final burst of diversity. By the final Changxingian age, only about 4 to 6 trilobite genera remained. Corals also declined through the Middle and Late Permian. On land, the Permian featured diverse plants, fungi, arthropods, and tetrapods. Much of vast Pangaea, especially in the northern hemisphere, was covered by arid deserts. Intense heat oxidized iron in exposed rocks, staining them reddish under the blazing sun. At the start of the Permian, plant life still resembled that of the Carboniferous, but major shifts began mid-period.
Moisture-loving tree-sized lycopods, including Lepidodendron and Sigillaria, started dying out. More advanced seed ferns and early conifers replaced them, especially inland where conditions were drier. This transition followed the collapse of Carboniferous rainforests. By the Permian's end, ancient swamp vegetation survived only on a chain of tropical islands called Cretaceous near the equator, in what would become South China. Meanwhile, conifers diversified significantly, with ancestors of many modern tree families emerging. In southern regions, vast seed fern forests, known as Glossopteris flora, thrived, possibly with high oxygen levels. This era also saw the appearance of ginkgos and cycads, both still alive today. During the Permian period, roughly 299 to 252 million years ago, insects already widespread in the Carboniferous experienced a new burst of diversity. Early Permian saw many new groups evolving in different directions. But towards the period's end, change slowed, with formation of new insect groups and extinction of old ones notably declining. An evolutionary arms race between insects and plants unfolded from early Permian onward. Insects developed increasingly complex ways to feed on plants, while plants evolved defensive structures protecting reproductive organs from damage. Fossil leaves show insect bite marks, and some plants developed tough outer spines to prevent being eaten. Common insects included early representatives of groups scientists called Paleoptera, Polyneoptera, and Paraneoptera. The large Paleodictyopteroidea group that dominated the Carboniferous began declining, likely due to fierce competition from newly emerged Hemiptera, which had similar piercing-sucking mouthparts and occupied comparable ecological niches. Another ancient group, Meganisoptera, containing the largest known flying insects, giant dragonfly relatives, also declined during the Permian. Meanwhile, Holometabola, insects with complete metamorphosis, including modern beetles, flies, butterflies, and bees, spread widely and diversified. Another now extinct group, Grilloblattida, reached its peak in the Permian, comprising about 1/3 of all insect species at some sites. These unusual forms are considered distant relatives of modern ice crawlers. Scorpion flies, or Mecoptera, first appeared in early Permian and became quite diverse by late Permian. Some, like members of the Mesozoic family, had long tubular mouthparts, suggesting pollination of ancient gymnosperms. The first beetles also appeared in early Permian. Early forms like Permocupedidae likely fed on rotting wood, and by the period's end, some beetles adapted to aquatic life. By then, representatives of modern beetle lineages existed: Archostemata, Adiphaga, and possibly Polyphaga, the last being today's most diverse beetle group. However, the Permian terrestrial fossil record remains quite fragmentary, with early Permian land fossils coming mainly from tropical regions of Europe and North America.
During the early Permian, primitive mammal-like synapsids dominated the land fauna of North America and Europe, particularly plant-eating adaphosaurids and predatory sphenacodontids. Alongside them lived diadastids, early reptile-like animals, and numerous amphibians. Small insectivorous reptiles like captorinids were also common. Synapsids, ancestors of mammals, grew increasingly successful and diverse throughout the Caesarean epoch. One of their most famous representatives was Dimetrodon, a predator with a tall sail on its back. Thanks to features like more efficient thermoregulation and complex teeth, synapsids thrived in the dry Permian climate and became the dominant land animals. But at the boundary between the Caesarean and the following Guadalupian epoch, the situation began to shift. Amphibians declined, while ancient synapsids, pelycosaurs, gradually gave way to more advanced therapsids. This transition was gradual, taking about 20 million years from the Artinskian age to the end of the Caesarean. As predators and prey evolved, their relationships became more complex and dynamic. However, gaps in the fossil record, especially at the Caesarean-Guadalupian boundary, make reconstructing the precise picture difficult. Some specialists identify what's called Olson's gap, which may reflect a global scarcity of fossil-bearing deposits. Others believe the North American and Russian records overlap more than previously thought, and some researchers even recognize a distinct extinction event from this time, Olson's extinction. In the Middle Permian, therapsids dominated the faunas of South Africa and Russia, especially the diverse dinocephalians. They vanished at the end of the Middle Permian during the Capetanian mass extinction.
In the late Permian, more advanced therapsids ruled terrestrial ecosystems, saber-toothed gorgonopsians and herbivorous dicynodonts with turtle-like beaks. Large pariasaurs also roamed the land. Another reptile group, archosauromorphs, distant ancestors of crocodiles, dinosaurs, and flying pterosaurs, first appeared and began diversifying in the late Permian. Archosauriforms, a subgroup of archosauromorphs, emerged at the very end of the Permian. Cynodonts, direct ancestors of all mammals, appeared and spread widely in the late Permian. Another therapsid group, Thyrocephalians, including lycosuchids, arose in the Middle Permian. Flying vertebrates did not yet exist, but some reptiles, such as Weigeltosaurids, had wing-like structures that allowed them to glide through the air. These gliding reptiles are considered the earliest known vertebrates capable of gliding flight. Temnospondylus reached their peak in the early Caesarean Permian, but many disappeared in the Middle and late Permian, especially after Olson's extinction. Another group, embolomirs, aquatic crocodile-like animals, were previously thought to have vanished earlier, but representatives have now been found in late Permian rocks of China. It's believed that modern amphibians, frogs, salamanders, and caecilians may have originated in the Permian from either disaurophid temnospondyls or lepispondyls. Fish diversity in the Permian was relatively low. Most bony fish belonged to the paraphyletic group Palaeoniciformes and did not yet belong to the modern Neopterygiae. The first true Neopterygians emerged in the early Triassic, though their evolutionary line likely began forming back in the Permian. Coelacanths showed little diversity for most of the Permian, but shortly before the mass extinction, their number of forms briefly increased. Freshwater fish fauna consisted mainly of lungfish and paleoniscoids. Lungfish in particular grew larger and more diverse in the early Permian, then declined later. Conodonts, jawless, eel-like animals used to determine geological boundaries, reached their minimum diversity during the Permian. Sharks and their relatives, the cartilaginous fish, aren't well studied for the Permian period,
but several groups stand out. Holocephalans, which include modern chimeras, were far more diverse in the Carboniferous and early Permian. Among them was the unusual helicoprion, a shark-like fish with a spiral tooth whorl.
Hybodonts and xenacanthiforms, both shark-like groups, were common in freshwater ecosystems and likely dominated them. Permian vegetation divided into four major floristic regions: Ungaran, Euramerican, Gondwanan, and Cretaceous. After the collapse of Carboniferous tropical rainforests, the once dominant tree lycopsids of Euramerica gave way to tree fern forests. In Gondwana, glossopterids, tall woody seed plants, dominated most of the Permian. The most famous representative, Glossopteris, probably grew in waterlogged, swampy soils, similar to modern bald cypress. Calamites, giant relatives of horsetails, grew in swamps as dense, almost bamboo-like thickets. The petrified forest of Chemnitz in Germany shows these plants already had complex branching resembling modern flowering trees by the early Permian. By the end of the Permian, forests of tall, slender trees had spread across much of the world. Global forest distribution is evidenced by widespread fossils of gliding reptiles, the Weigeltosaurids. The earliest probable member of the ginkgo family, Trichophytis heteromorpha, appeared in what is now France at the very beginning of the Permian. The oldest confirmed fossils of modern cycads date to the late Permian. In warm, frost-free tropical Cretaceous, Nogarithiales, an extinct group of tree-like plants, grew widely. The fossil plant community of this region shows a multi-layered swamp forest. Lycopsids like Sigillaria towered above, with tree ferns and numerous Nogarithiales growing below. Conifers, which first appeared in the late Carboniferous, became more widespread and better adapted to dry climates during the Permian, increasingly resembling modern conifers. As aridity intensified, especially at low latitudes, these drought-resistant trees occupied ever larger areas of land. Benedictales, destined to become an important part of Mesozoic flora, first appeared in China during the Caesarean epoch. Meanwhile, Lygenopterids, older groups of seed ferns that had declined by the late Carboniferous, persisted in certain areas of Cretaceous and eastern Gondwana until the late Permian. The Triassic period holds an important place in Earth's geological and paleontological history. It lasted approximately 50 million years. The Triassic began roughly 252 million years ago, right after the catastrophic end of the Permian, and wrapped up around 201 million years ago when the Jurassic kicked off. It was the first and shortest period of the Mesozoic era, and sat between two devastating mass extinctions that reshaped life on Earth. The period is split into early, middle, and late epochs. Its story starts in the aftermath of the worst biological disaster our planet has ever seen, the Permian Triassic extinction, which wiped out most life. But from that wreckage, new life slowly emerged, often in completely unexpected ways. Triassic fossils reveal three broad groups: tough survivors from the Permian catastrophe, short-lived Triassic forms that briefly flourished then vanished, and long-term winners like dinosaurs and early mammals that would shape life for millions of years to come. Reptiles ruled the land, especially archosaurs, the ancestors of crocodiles, birds, and dinosaurs. Dinosaurs appeared late in the Triassic, but hadn't yet claimed the dominance they'd achieved in the Jurassic. The real power players were pseudosuchians, crocodile-like archosaurs in a stunning variety of shapes and sizes. Some archosaurs took to the sky, becoming pterosaurs, the first flying vertebrates with leathery wings stretched between elongated fingers. Before archosaurs rose up, the main land animals of the Permian had been therapsids,
the mammal-like reptiles. A few, like dicynodonts and cynodonts, briefly bounced back in the Triassic but gradually declined, most disappearing by period's end. Yet from cynodonts came something remarkable: early mammals. These tiny, shrew-like creatures were flexible and adaptable. Staying small and out of sight, they survived and would later thrive. Amphibians also got their moment. Giant semi-aquatic predators called temnospondyls survived the Permian crisis and diversified again before eventually dying out. Meanwhile, the first representatives of modern amphibian groups, early frogs, salamanders, and caecilians, appeared and made it through the next great extinction. In the water, neopterygians, the ancestors of modern bony fish, appeared early and spread rapidly, becoming key inhabitants of both freshwater and ocean environments. Earth's continents were still joined into one massive supercontinent, Pangaea, stretching nearly pole to pole and surrounded by endless ocean. Its interior regions sat far from the moderating influence of the sea, creating extreme seasonal swings, scorching summers followed by freezing winters. Most of the land was dry and desert-like, especially the center. Yet the polar regions weren't ice-covered.
They enjoyed a moist, temperate climate with forests and reptiles. No glaciers from this time are known on Earth. Pangaea's enormous size created powerful monsoons crossing the equator, massive weather systems sometimes called Pangaean megamonsoons that swept across the supercontinent from edge to edge. Though the Triassic was generally dry, wetter phases periodically arrived, especially in the tropics near the Tethys Sea. Fossil and sediment layers from Spitsbergen, North America, South China, and Argentina show these wet episodes repeated many times. The most powerful was the Carnian pluvial episode, a sharp spike in rainfall and humidity during the Carnian stage of the late Triassic that may have triggered ecosystem shifts worldwide. The early Triassic was one of Earth's hottest periods, linked to massive greenhouse gas releases from the Siberian Traps eruptions. It began with the Permian Triassic thermal maximum, followed by a brief Dinarian cooling from about 251 to 249 million years ago. Temperatures then surged again during the late Smithian thermal maximum around 249 to 248 million years ago, before another short, late Olenekian cooling dropped temperatures roughly 6 degrees Celsius. The Middle Triassic was cooler overall, though a warming episode occurred near the end of the Anisian stage. A longer Ladinian-Carnian cooling lasted from approximately 242 to 233 million years ago. Global temperatures stayed moderate in early Carnian times, but around 234 million years ago, eruptions from the large Wrangellia magmatic province heated the atmosphere and triggered the Carnian pluvial episode. This brought a warm, wet phase, the mid-Carnian warm interval, lasting until roughly 227 million years ago. The early Norean cold interval brought renewed cooling from 227 to 217 million years ago, followed by the mid-Norean warm interval continuing to about 209 million years ago. Around 214 million years ago, a brief cold episode may have occurred, possibly linked to the Manicouagan meteorite impact. About 212 million years ago, changes in Earth's orbit expanded swampy areas and reduced arid zones. Then came the Rhaetian cold interval, lasting from 209 to 201 million years ago.
At the very end of the Triassic, Earth endured another extreme heat wave, the End Triassic thermal event, caused by massive eruptions from the Central Atlantic magmatic province that released enormous amounts of carbon dioxide into the atmosphere.
The result was the Triassic-Jurassic extinction, a new global biological crisis that cleared the path for dinosaurs' complete dominance in the Jurassic. After Earth's greatest extinction event, life began recovering in the Triassic, which started around 252 million years ago. But the world had changed. Hotter, drier, filled with unfamiliar landscapes. Organisms that survived the extinction had to adapt to a completely different planet. In the very early Triassic, ancient spore-bearing lycophytes spread widely, especially quillworts, relatives of modern isoetes. The most famous was Pleuromia, a tall, straight green column sometimes reaching 2 meters, about the height of an adult human. These plants thrived in the unstable environment immediately after the extinction, but as the climate stabilized in the Middle Triassic, they began to decline. A new type of seed plant, the Benetitales, first appeared in the Permian and spread widely across Earth during the late Triassic, becoming a key part of Mesozoic flora. In the southern continents of former Gondwana, forests were often dominated by the unusual Dicroidium, an extinct seed fern from the Corystosperm group, especially common in the Middle and Late Triassic. Meanwhile, ginkgos began to diversify and spread, a group with only one surviving species today, Ginkgo biloba. Triassic forests were rich in conifers, including the extinct Voltziaceae and the Chiralepidiaceae family, which first appeared in the late Triassic and spread widely throughout the Mesozoic. Curiously, no coal deposits are known from the earliest Triassic. This mysterious gap in coal formation, called the Early Triassic Coal Gap, is linked to the mass extinction. Possible causes include falling sea levels, acid rain from Siberian eruptions, global warming drying out swamps, or the disappearance of swamp plants with a long delay before replacement species appeared. Oxygen content in soils may have also dropped sharply, making it difficult for peat, coal's raw material, to form. In the oceans, a new generation of corals began growing, though their reefs remained small compared to modern ones or the massive Devonian systems. By the end of the Carnian, coral communities in what is now southern China experienced a sudden crisis. Meanwhile, other marine animals appeared and thrived. Serpulids emerged in the Middle Triassic, and tube-dwelling microconchids were widespread. One major success story was the return of ammonites, shelled relatives of squid and octopuses, which recovered from near-total extinction and began flourishing again. Bivalve mollusks, including ancestors of modern clams and mussels, also diversified rapidly in the Middle Triassic and became a dominant group in marine fauna. In freshwater, many new insect forms appeared. Particularly important was the rise of holometabolous insects, the group with complete metamorphosis that includes most modern insects like beetles, flies, butterflies, and bees. Fish communities in oceans, rivers, and lakes began recovering actively. After the extinction, many fish species were similar worldwide, what scientists call a cosmopolitan distribution. The ancient coelacanth group, thought nearly extinct, reached its greatest diversity since the Devonian in the early Triassic. Ray-finned fishes, or actinopterygians, also experienced a powerful surge in diversity during the Triassic, especially mid-period. Among new forms were the first teleosts, which today are the most diverse fish group. Some ray-finned fishes, like saurichthiids and bergerids, were fierce predators, growing over 1 meter 20 centimeters long.
In freshwater lakes and rivers, lungfish like Ceratodus were common, known mainly for their powerful tooth plates. Another group was the hybodonts, shark-like fishes that dominated both fresh and marine waters throughout the Triassic. The unusual ancient cartilaginous fish, Eugenodontida, briefly survived into the early Triassic before disappearing completely. Temnospondyls also survived the mass extinction and continued existing in the Triassic. Terrestrial amphibians mostly vanished, but aquatic ones survived. Early species like Tupalachosaurs, Trematosaurs, and Microphyllus disappeared in the early Triassic, while stereospondyls thrived. Some even lasted into the Cretaceous. The largest, like Mastodonsaurus, reached 4 to 6 meters long. The first modern amphibians, lissamphibians, emerged during this time. Frog ancestors existed in the early Triassic, but only spread widely in the Jurassic after temnospondyls declined. Reptiliomorphs, early vertebrates close to the first reptiles, nearly disappeared.
Only 2 aquatic groups remained: Embolomeres, which soon died out, and Croniosuchians, which lasted until the period's end. After the catastrophe, a new reptile group took over, Archosauromorphs. Their evolution began in the Permian, but freed ecological niches triggered explosive diversity. Among them were Proterosaurs, long-standing, lizard-like animals. The most famous, Tanystropheus, had a neck longer than its body. Cherovipterygids had long hind limbs, possibly used for gliding. Other archosauromorphs, like rhynchosaurs and alacodosaurs, were herbivores. Rhynchosaurs had barrel-shaped bodies and beaked mouths lined with teeth. They were abundant in the Middle Triassic, but vanished around 220 million years ago. Alacodosaurs included Trilophosaurus with 3-cusped teeth, long-snouted Pteroturpeton, and horned Shringosaurus, about 3 to 4 meters long. Key archosauromorphs were archosauriforms, fast predators with sharp teeth and limbs positioned directly under their bodies. In the early Triassic, large-headed erythrosuchids topped the food chain. Later, phytosaurs became widespread. They resembled crocodiles and likely lived similarly, ambushing fish and reptiles in water. But this was convergent evolution, not close kinship. True archosaurs, the group that later gave rise to dinosaurs, birds, and crocodiles, split into 2 main branches in the early Triassic: Avametatarsalia, the bird line, and Pseudosuchians, the crocodile line. Initially, bird-line archosaurs played minor roles, but by the late Triassic they'd produced pterosaurs, the first flying reptiles, and dinosaurs. The first dinosaurs appeared in the Carnian age, small predators like Coelophysis, 1 to 2 meters long. Early herbivorous sauropodomorphs lived mainly in cooler regions. The enigmatic large predator smoke may have been an early dinosaur or a crocodile relative. Its position remains uncertain. Meanwhile, Pseudosuchians, the crocodile line, dominated land. These included armored herbivorous atosaurs, enormous predatory Rauisuchians, and the first small, agile crocodilomorphs. Rauisuchians were the Triassic's top predators, ranging from giant quadrupedal hunters to bipedal forms with tall back crests. After the Triassic ended, only crocodilomorphs from this line survived the crisis into the Jurassic and beyond. In Triassic oceans, many remarkable marine reptiles lived. One major group was Sauropterygians, including Pachypleurosaurs and Nothosaurs.
Both were especially common in the Middle Triassic, primarily in the warm tropical waters of the Tethys Ocean. Zavropterygians included placodonts, massive creatures with powerful jaws built for crushing shells.
and the unusual Atopodentatus, the earliest known marine herbivore. This group later gave rise to the first plesiosaurs, famous for their long necks and paddle-like limbs. Around the same time, other reptiles like the elongated thalattosaurs entered the seas, with Askeptosaurus among the early examples. Another key group was the ichthyosaurs, which somewhat resembled modern dolphins. They appeared in the early Triassic oceans and quickly diversified. By the Middle Triassic, some ichthyosaurs had grown enormous, becoming among the largest marine animals of the era. On land, the first turtles emerged in the Nourian age of the late Triassic, roughly 220 million years ago. Early turtles like Proganocalus and Protoricursus already possessed hard, protective shells. During the Carnian age of the late Triassic, Lepidosauromorphs began appearing, the group that would eventually give rise to modern lizards and snakes, though their ancestors likely existed much earlier, possibly back in the Permian. Among the stranger reptiles were the Drepanosaurids, small, tree-dwelling animals with chameleon-like bodies, bird-like beaks, and claws adapted for gripping branches. Procolophonids were another group of small, lizard-like plant eaters, the last survivors of an ancient reptilian lineage that remained ecologically important right up to the end of the Triassic. Three groups of therapsids, the beast-like ancestors of mammals, survived into the Triassic: Dicynodonts, Therocephalians, and Cynodonts. The cynodont Cynognathus was a fierce predator widespread across the southern parts of Gondwana during the Olenekian and Anisian ages of the early and middle Triassic. Among herbivores, Cannemyriaform dicynodonts and Gomphodont cynodonts were especially important, grazing across Triassic plains. Therocephalians included large predators like Moscarinus and herbivorous Bauriids, though the group went extinct by the Middle Triassic. In the late Triassic, a new group of large, fast, predatory cynodonts emerged, the ectoniniids. During the Carnian age, some advanced cynodonts gave rise to the first mammals, a pivotal moment in Earth's history. Meanwhile, archosaurs grew increasingly dominant.
This group included the ancestors of crocodiles, pterosaurs, and dinosaurs, becoming the largest and most successful land animals of the Triassic, and pushing therapsids into narrower ecological niches. This shift, sometimes called the Triassic takeover, may have driven mammalian evolution. As therapsids and their descendants literally found themselves in the shadows, they became smaller, adopted nocturnal habits, and increasingly fed on insects. This likely spurred the development of fur for warmth and higher metabolism needed for nighttime activity. Two remarkable early Triassic fossil sites give scientists an exceptionally detailed picture of life after the Permian-Triassic mass extinction. Such sites are called Lagerstätten, locations with exceptional fossil preservation. One is the Guiyang biota from the Dinarian age, the other the Parisian biota from the very beginning of the Spathian age. Both provide valuable insights into how life gradually recovered after the greatest extinction in Earth's history. Monte San Giorgio, on the shores of Lake Lugano between northern Italy and southern Switzerland, is another significant site. During the Middle Triassic, a calm, shallow lagoon existed here, sheltered by coral reefs. The lagoon floor had little oxygen, which meant almost no scavengers or bottom disturbances. Dead animals were preserved exceptionally well, similar to the famous Jurassic Solnhofen limestone. Many marine organisms have been found at Monte San Giorgio, including fish and diverse marine reptiles like Neotocosaurus, Pachypleurosaurs, and the unusual long-necked Tenestropheus, which may have caught fish near shore with its incredibly long neck. Remains of land animals such as Tichinasuchus and Macrocnemus have also been discovered.
These creatures lived during the Anisian and Ladinian ages, roughly 242 million years ago. The Jurassic period became the next major chapter in Earth's history. It began around 201 million years ago after the Triassic ended and lasted until about 143 million years ago when the Cretaceous began. The Jurassic was the second middle period of the Mesozoic era. The name comes from the Jura Mountains, where scientists first studied thick limestone deposits from this age. The period began after a mass extinction at the end of the Triassic, likely caused by massive eruptions from the Central Atlantic Magmatic Province.
Another dramatic event occurred around 183 million years ago, the Toarcian Oceanic Anoxic event, when oceans lost much of their oxygen, became more acidic, and Earth's temperature spiked, probably due to large-scale volcanism in the Karoo and Ferrar provinces in what is now South Africa and Antarctica. By the early Jurassic, Pangaea had begun splitting into Laurasia in the north and Gondwana in the south. The climate was much warmer than today, with no polar ice caps and forests near the poles. Huge arid zones stretched across the equator, while lush forests grew elsewhere. Dinosaurs, which had appeared in the Triassic, now dominated the land, displacing many other reptile groups. The first early birds evolved from small predatory dinosaurs. The Jurassic also saw the first frogs, salamanders, lizards, and crabs. Mammalia forms, the ancestors of mammals, began diversifying rapidly. Crocodilomorphs moved from land into water. Large marine reptiles like ichthyosaurs and plesiosaurs were common in the oceans, while pterosaurs ruled the skies. Modern shark and ray lineages appeared and spread. Near the period's end, teleosts, an extremely important modern fish group, emerged. Plant life consisted mainly of ferns and gymnosperms, especially conifers. The extinct Bennettitales were also widespread. The Jurassic climate was generally warm, about 5 to 10 degrees Celsius warmer than today, with roughly 4 times more atmospheric carbon dioxide. Despite the overall warmth, cooling periods occurred, especially in northeastern Siberia, where winters could be freezing. The deep ocean was warmer too, and coral reefs grew closer to the poles than they do now. Most non-arid land lay between 40 degrees north and 40 degrees south latitude. Rainforests and tundra were rare, and large ice sheets probably didn't exist because summers were too warm for snow to accumulate long-term. Still, glaciers may have existed in high mountains. Throughout the Jurassic, the climate shifted repeatedly. Right at the start, Earth warmed sharply after the Triassic extinction. Then, from roughly 199 to 183 million years ago, came the early Jurassic cool interval. Some scientists think there may have been brief glaciations. Around 183 million years ago, Earth heated up again during the Toarcian warm interval, with temperatures in some regions reaching 40 degrees Celsius or higher. Near the equator, ocean temperatures exceeded 30 degrees Celsius. After that came the Middle Jurassic cool interval from about 174 to 163 million years ago, possibly with short-lived glaciations. Later, during the Devonian age, Europe became briefly wetter before drying out again. Another possible short glacial episode occurred in the late Bajocian. One of the coldest phases hit at the boundary between the Colovian and Oxfordian ages, when Earth may have experienced glaciation once more. Then began the warmer Kimmeridgian interval, from roughly 164 to 150 million years ago, possibly one of the wettest stages of the Jurassic.
As the Atlantic opened, more moisture reached interior regions and seasonal extremes weakened. Near the end of the Jurassic, the early Tithonian cooling began, transitioning into the longer Tithonian to early Permian cool interval that extended into the early Cretaceous. One of the most dramatic events of the Jurassic was the Toarcian oceanic anoxic event. It happened in the early Toarcian age, around 183 million years ago, and brought severe oxygen depletion in the oceans, global warming, and high carbon dioxide concentrations. Many marine animals died off, especially shelled organisms like brachiopods, though marine reptiles were barely affected. During this event, a massive lake formed in the Sichuan Basin in what is now China, possibly 3 times the size of modern Lake Superior, locking up enormous amounts of carbon. The oceans became more acidic, and many tiny marine organisms lost the ability to form shells. An additional influx of phosphorus worsened the oxygen shortage, triggering feedback loops that intensified anoxic conditions. The end of the Jurassic wasn't marked by a clear mass extinction, but it was a time of major change. Some animal groups grew in number, others declined. Dinosaurs, which had begun diversifying in the late Triassic, became even more successful in the early Jurassic and spread wider. Many new theropods appeared, including early relatives of T-Rex like Proceratosaurus, as well as unusual forms like Limosaurus, a beaked dinosaur that lost its teeth and became herbivorous. Feathered dinosaurs evolved too, including early Scansoriopterigids with wings resembling those of bats. True birds appeared by the middle to late Jurassic. One of the oldest known examples is Archaeopteryx from Germany.
Among herbivorous dinosaurs, the early Jurassic saw the emergence of early ornithischians like Lasutosaurus and the heterodontosaurids. Later came ankylosaurs, stegosaurs, and other armored dinosaurs. Some, like Kulindodromeus from Russia, had feathers or feather-like covering. The first horned dinosaurs, ceratopsians, appeared in China. Sauropods, the largest land animals ever, reached gigantic sizes in the Jurassic. Some weighed 12 tons or more, like Ledumahati from South Africa. Earlier, small bipedal relatives mostly disappeared by the Middle Jurassic. Landscapes were dominated by giant sauropods like Vulcanodon, Cetiosaurus, and Mamenchisaurus. By the late Jurassic, groups like Diplodocids and Brachiosaurids spread worldwide. Crocodile-like pseudoseuchians mostly vanished at the end of the Triassic, except for crocodilomorphs, which survived and thrived. In the Jurassic, these animals evolved many new forms and lifestyles. Some stayed terrestrial, others became fully aquatic. The Latisuchia even developed flippers, tail fins, and smooth, dolphin-like skin. Another group, Neosuchia, became ancestors of modern crocodiles and began adapting to freshwater. The oldest known Neosuchian may be Chalcoiasuchus from Arizona, though its exact position remains debated. Other ancient crocodile relatives, like Rhizanendron gobi from Madagascar, may belong to a predominantly southern group of Notosuchians. The Cretaceous was one of Earth's most remarkable chapters. It began around 143 million years ago and ended approximately 66 million years ago. This was the third and final period of the Mesozoic era, after the Triassic and Jurassic. The Cretaceous was not only the final chapter of the dinosaur age, but also the longest period of the entire Phanerozoic eon, lasting about 77 million years. The name comes from the Latin word creta, meaning chalk, since enormous amounts of chalk rock formed especially in the later part of the period. Ancient chalk deposits can still be seen today, for example, in the White Cliffs of Dover in England. The Cretaceous climate was warm, much warmer than today.
Large polar ice caps didn't exist, and sea levels were so high that vast, shallow seas flooded the interiors of many continents. These warm shallows teemed with unusual creatures, spiral-shelled ammonites, reef-building rudist bivalves, and now extinct marine reptiles. On land, dinosaurs still dominated in all shapes and sizes.
Dense forests reached polar regions. The roots of many modern groups of animals and plants trace back to the Cretaceous. New mammals and birds appeared, including early ancestors of placentals and marsupials, lines from which later arose animals like humans, kangaroos, and whales. True birds with feathers and flight increasingly resembling modern forms developed. In the seas, teleosts flourished, the group to which most fish from goldfish to tuna belong today. One of their most diverse lines, acanthomorphs, was especially active during the Cretaceous. One of the most important events in life's history was the spread of flowering plants or angiosperms. Today, they make up about 90% of all plant species, and in the Cretaceous, they began rapidly blooming and spreading across the world. In the early Cretaceous, flowering plants remained small, but then rapidly spread, displacing older seed-bearing gymnosperms like conifers, cycads, and ginkgos. By the end of the period, angiosperms had become Earth's dominant vegetation. The oldest known flowering plant pollen grain with a single furrow was found in Israeli and Italian rocks dating back around 134 million years. Later, roughly 90 million years ago, some early large angiosperm trees reached 50 meters in height, with trunks nearly 2 meters thick. Grasses, which belong to flowering plants, also appeared in the Cretaceous. Their oldest fossils date to the Albian Age, approximately 110 million years ago. Around this time, ferns of the order Polypodiales began spreading. This order includes most modern fern species. Though Cretaceous mammals remained mostly small, they played important roles in ecosystems. In some areas, multituberculate mammals were even more common than dinosaurs. These early mammals occupied many niches. Some were predators, others herbivores, and some even adapted to aquatic life. True marsupials and placentals appeared only near the very end of the Cretaceous, but their early relatives were already exploring different lifestyles. Dinosaurs, naturally, remained the undisputed dominant land predators. During this time, numerous Maniraptorans developed, a group including birds and their closest dinosaurian relatives like dromaeosaurs, oviraptorosaurs, and therizinosaurs. Fossils from China's Yixian Formation preserved stunning details, including feathers on many animals, offering a rare glimpse into ancient life almost directly. Pterosaurs were widespread in the early and middle Cretaceous, but their diversity declined toward the period's end. Only a few specialized families survived to the final stages: pteranodontids, nyctosaurids, and azhdarchids. Insects also experienced a true flourishing. The earliest ants, termites, and butterflies appeared, along with aphids, grasshoppers, and gall wasps. Some other ancient animals, however, began disappearing. Rhynchocephalians, relatives of the modern tuatara, vanished from many regions, likely due to competition with more advanced lizards and mammals. Yet in certain southern areas, especially South America, they remained abundant, and in places outnumbered lizards by roughly 200 to 1. Another interesting group, Choristoderes, freshwater reptiles somewhat resembling crocodiles, thrived in Asia during the early Cretaceous. Some had long necks, like the unusual Hyphalosaurus, while Neochoristoderes strongly resembled modern gharials. By the late Cretaceous, Champsosaurus had spread across much of western North America. Thanks to the warm climate, these animals reached even the Arctic.
The Cretaceous period ended dramatically about 66 million years ago, when a massive asteroid struck the region of the modern Gulf of Mexico, leaving the giant Chicxulub crater. The impact triggered the Cretaceous-Paleogene extinction, one of the most devastating mass extinctions in Earth's history. Non-avian dinosaurs, pterosaurs, large marine reptiles, and countless other life forms vanished almost instantly by geological standards. This catastrophe marks the sharp boundary between the Mesozoic era and the beginning of the Cenozoic, the age of mammals and flowering plants that continue shaping our world. Rays thrived alongside modern sharks and advanced bony fish called teleosts. The seas were home to various large reptiles. Ichthyosaurs, which looked somewhat like dolphins, were common in the early and middle Cretaceous, but disappeared during a major oceanic crisis near the period's end, the Cenomanian-Turonian anoxic event. Long-necked plesiosaurs with flipper-like limbs existed throughout the Cretaceous. Later, giant marine lizards called mosasaurs emerged as the ocean's apex predators. Marine turtles also inhabited Cretaceous seas. Two groups, cheloniids and panchelonioids, survived the mass extinction at the period's end. Today, only one panchelonioid species remains, the leatherback turtle, the largest living sea turtle.
Flightless seabirds called Hesperornithiformes swam like modern grebes, diving and chasing fish with powerful legs. Among the shelled sea creatures, baculites and ammonites with long, straight shells were particularly notable. Rootists, reef-building bivalves, played a crucial role in creating underwater reefs. Another important bivalve group was the inoceramids, especially widespread in the Cretaceous. Scientists often use them to study major changes in ancient life, particularly near the Turonian-Coniacian boundary. The seas teemed with predatory gastropods that drilled through other animals' shells using specialized mouthparts. Tiny single-celled foraminifera, especially globotruncanids, floated in the oceans and became extremely numerous. Echinoderms like sea urchins and starfish flourished. Small crustaceans called ostracods were everywhere, though interestingly, species investing more resources in reproduction, especially through males, faced higher extinction risk. A mysterious crustacean group called thylakocephalans disappeared by the Cretaceous's end. Meanwhile, microscopic algae called diatoms with glassy silica shells spread rapidly through the oceans, though freshwater diatoms only appeared much later in the Miocene. Calcareous nanoplankton also played a major role, helping form seabed deposits and allowing scientists to track environmental changes in ancient seas. The Cretaceous marked an important stage in bioerosion development, the process where marine organisms drill into rocks, shells, or hardened seafloor, leaving traces scientists can study. On land and beneath the oceans, Earth's face and continental positions changed dramatically. Massive Pangaea, which began breaking apart in earlier epochs, finally split completely during the Cretaceous. The landmasses destined to become modern continents moved along their own trajectories, though their positions still differed greatly from today. As the Atlantic Ocean expanded, Western North America experienced a series of mountain-building events, the Novaton, Severe, and finally Laramide orogenies. The southern supercontinent Gondwana began fragmenting in the Jurassic, but separation accelerated during the Cretaceous and was nearly complete by the period's end. South America, Antarctica, and Australia separated from Africa, though India and Madagascar remained connected until about 80 million years ago.
This rifting created new oceans, the South Atlantic and Indian Ocean, and raised enormous underwater mountain ranges. These shifts triggered a worldwide sea level rise. North of Africa, the Tethys Sea began narrowing,
For most of the late Cretaceous, a massive interior basin, the Western Interior Seaway, split North America, separating Laramidia in the west from Appalachia in the east. This seaway later retreated, leaving thick marine deposits between coal-bearing layers. In Africa, the fossil record reveals that during the Cenomanian and Santonian ages, a shallow sea also cut across the continent, running through what is now the Central Sahara and other parts of Central Africa, linking the Tethys in the north to the South Atlantic. Another shallow strait existed between present-day Norway and Greenland, connecting the Tethys to the Arctic Ocean and allowing marine life to migrate between basins. At peak sea levels during the Cretaceous transgression, roughly 1/3 of today's land lay underwater. The Cretaceous is especially famous for its chalk deposits. More chalk formed during this period than at any other time in the last 540 million years of the Phanerozoic. As underwater ridges grew and seawater circulated through their rocks, the ocean became enriched with calcium. This made it easier for planktonic organisms to build calcium carbonate shells, which settled on the seafloor and formed thick chalk layers. Cretaceous rocks are therefore often well preserved and rich in fossils. In North America, notable formations include the Smoky Hill Chalk in Kansas, abundant with marine fossils, and the Hell Creek Formation, famous for late Cretaceous land animals, including dinosaurs. In Europe, important Cretaceous rocks are found in the Weald region of England. In China, the Xian Formation has yielded numerous beautifully preserved fossils from this time. In what is now India, massive eruptions formed the Deccan Traps, extensive lava fields whose eruptions began at the very end of the Cretaceous and continued into the early Paleocene, with basaltic eruptions recurring in this region over roughly 800,000 years.